we go ahead and get started? There's a few folks, but the important ones are here, right?
Yes.
So there we go. We're getting everybody else in. So we're going to start off with a student presentation for quantum computing, and then we'll have David, our guest speaker. So I'll kick it over to you guys. Is this the whole team?
Yes.
Yeah, okay.
Perfect. Thanks.
So hello everyone. I'm Simar and he's Jason, and we are presenting on quantum computing. I would just like to begin with a small story about how I got introduced to quantum computing. It was around 10 years back in 2013 when I was an undergrad student and fresh in college, and there was this professor who was teaching physics, and he was like, all the classical physics that you have read till now the knowledge needs to be updated. There's this quantum physics and you cannot travel faster than the speed of light. And that was my first introduction. And then again in 2019, Google announced that some quantum supremacy video, and I was super intrigued by that and started watching YouTube like Vertasium and other channels to learn more on quantum computing. And this is my third chance to learn about quantum computing. So I just took that opportunity, and yes. So starting with how a quantum computer is known to most of us. I'll get this. So this is how a traditional quantum computer image is known for us, but now IBM has made great advancements in this. So this is the Osprey. It is of 433 qubits, which is a very big number. We have made huge progress in that. And on the right side, we can see Jay Gambetta, who's an IBM fellow and VP of IBM Quantum. So I was just watching one of his talks and saw that it has come from such big to such a small device with 433 qubits. And obviously the cooling mechanisms must be larger. So I'll hand it over to Jason for the history and explanation of quantum computing.
Yeah, thank you, Samar. So just a quick recap on how it all started. We looked into how quantum mechanics has first started, right? So early in the 20th century, there were the foundations of quantum mechanics that were discovered, very important physicists. And as you go through, you talk about Heisenberg, Schrodinger, right? And all these important physicists who made discoveries in quantum mechanics that kind of started this revolution of how we got to where we are today, right? So in the 80s, there were propositions. In the 90s, you saw IBM started developing and investing money into this field. And then more recently, we see significant advances. And if you look at the timelines that are proposed by IBM, it's actually pretty aggressive. And it's done by, all the market leaders, which we'll be discussing later. So let's talk about that progress that I was talking about. It's more than exponential, right? So you talk about 1997, we had maybe 1 or 2 qubits. And now we're at 443. And by the end of 2023, the proposals have almost 1,000 qubits, which is a significant number from a quantum perspective. So you might be wondering, what is quantum computing? How is this relatable to me? So I thought maybe these 4 topics as an intro would be kind of enlightening for a lot of you to get a better understanding of what quantum computing really does. So I'll be discussing what a qubit is, what is a superposition, entanglement, and measurements. So what's a qubit, right? So we talk about these bits and zeros and ones that we see in classical computing, but from a quantum perspective, you have a qubit that has zeros, ones, and as well as this position called superposition, where it's a combination of those 2 specific bits, right? So what does that mean? So go back 1 slide. What does superposition mean? So you need to look back at what quantum mechanics is. And, I might be giving a little bit of a false explanation here, I'm sure you can correct me, but basically think of like Schrodinger's cat, right? So you look at this box, and before you decide if the cat is alive or dead, you say, okay, it must be one or the other, and we don't know what state that's in. And as you open the box, you're able to discover if that cat is alive or dead, and that's kind of similar to what a qubit is. And these qubits and that superposition are determined by these vectors. So you can have a probabilistic model of, hey, is it going to be a 0 or a 1? And when you observe that, as you go to the next slide, when you measure that, then you'll be able to collapse that superposition into a 0 or 1 to determine, okay, we had this qubit, it was in this superposition, and had these probabilities of being a 0 or 1, and when we observe it, it actually becomes a 0 or 1. And then we talk about entanglement. So, what is entanglement? In order to make these super position quantum qubits effective, you need to tangle them together so that you get the outcome that you're looking for. So when you have one qubit, there's only really 0 or 1 that it could become, but when you have a series of qubits, say 433, and you entangle a few of them, now you can get outcomes that are more complex. You can have different outcomes where, if this condition occurs, then these two qubits work together to solve a specific problem. Right, next. So, who's in the market today and how is that relevant for us? So, IBM obviously is a leader in this field right now. They're doing a lot of open source quantum computing, such as QZ. You can go online today and try it out yourself. Google is a competitor, and a lot of these other companies are also working on the hardware and the software side. And there's other companies too that are taking quantum in a different way. So right now, a lot of companies, especially IBM, are doing it in these very cold states. There are other companies not trying to do that and trying to have it out in the open field. So it's going to be interesting to see how that field evolves. Some future applications, life sciences, right? We talk about pharmaceuticals and how chemical interactions of drugs occur in the human body. Like, for example, today, in classical computing, you can't really model like caffeine as a drug, right? Because it's too complex of a model. But now with quantum computing, we're able to change that and actually model how that would behave in certain atmospheres or certain environments. Financial services, Monte Carlo simulations is the classic example, right? Because you're taking a lot of random variables and seeing how that affects the risk of the market. Cryptography and security is one of the biggest. I'm sure many of you have heard of Shor's algorithm. It's basically RSA encryption for basically a lot of what we do in, let's say, like your passwords and hashing algorithms that determine, okay, you have, millions of years it'll take to break a password. But with quantum computing, Shor's algorithm makes it so that it's a log regression, meaning instead of taking exponential amount of time for each bit, it would be a log regression. So as you increase the number of qubits, you'll be able to break some of the encryption algorithms that we have today. All right, so let me pass it back to Samar to kind of go back.
Thank you so much, Jason, for the great introduction. So, who are the countries that are currently leading the quantum wave? So, as students of business, that is important for us. How can we get involved in the quantum wave? So, currently it is China. Like, China is like 15%, like in terms of public funding, and even in terms of the largest number of patents that countries have. United States is very low, as we need to catch up. So we are currently only at 2% in terms of funding. So yeah, let's move to the next slide. So as students, like, what are the market opportunity for startups? So as we can see that from 2021 to 2022, the funding has almost doubled in startups in the quantum space from 0.7 billion to $1.4 billion. So there's obviously traction in this space, and which is the areas that are getting traction is on the right side of the screen. So like here we can see that there are 5 typical opportunities: components, hardware, system software, application, and services. The area that is growing very fast now is application software. That is an area that is getting funding, and hardware is obviously started to pick up. The journey has been very slow till 2017, and now it has started to pick up with since we are able to access more qubits. So now, what are the challenges for quantum computing right now? So scaling to a large number of qubits is a big challenge. Building stable and reliable computing is one of the biggest challenge now, because there's a lot of noise and errors that happens in the quantum systems right now. So integration with classical systems. The classical computers still are very important. So their integration is going to be a challenge, and public availability of quantum computing. So now we'll go through what is one of the biggest players, IBM, doing to address these challenges. So IBM's role in addressing these challenges they are looking at scale. So they have already scaled to 433 qubits till now. They are looking on quality, like how they can reduce the noise. And I would let David speak on some of these areas in his talk. So, like, what is the carbon footprint of computing footprint of IBM? So it is currently has 34 innovation centers. I was surprised to see that one innovation center is also in IIT Madras. Like that's in India, the place that I come from. So yeah, pretty cool. And these are the applications that integrate us in the quantum space on the right hand side. Yeah. So what is the role that IBM is playing for the adoption of quantum computers? So there are almost 460K plus students who are registered on their website. 5 million plus students have accessed that learning content, and even they have partnerships with universities to for making students involved in quantum computing. And even now, like they are getting involved with cloud providers like Azure and AWS, such that quantum is available as a service. You just go to the cloud and deploy your quantum workload. So with this, I would like to move towards our speaker introduction. So please welcome David Bryant. He is the CXO of design of quantum computing, responsible for product design and marketing. So he took IBM quantum computing out of the lab and turned it into one of the most successful quantum computing business in the world. He has 2 patents in the quantum computing space, and a very recent one, I guess, in the last month has been the first truly commercial quantum computing design. So he has been a pioneer in this space and has worked with 2 companies in quantum computing, first Rigetti Computing and now with IBM. So David did his bachelor's in computer science from King's College, London, but after that he moved towards the creative side of field and has worked for over 20 years in companies such as Google, Digitus and Publicis. He has also co-founded a couple of companies such as Havoc, Special Forces. He currently lives in NYC, and yeah, he's pretty excited about this space. So with this, I would hand it over to David for his talk.
Good evening, everybody. I can hear you. Okay, how's everybody doing? All good? Okay, all right. So I'm David Bryant from IBM Quantum. I'm here to talk to you about quantum computing. Before I talk about what I'm going to talk about, I'm going to talk about what I'm not going to talk about. I'm not going to talk about quantum mechanics. I think you'd be happy to hear that. I'm not going to talk about superpositional entanglement. Thank you for the introduction. I'm not going to talk about spooky interaction and distance. If you haven't heard that phrase, that's what Einstein referred to. Can't hear? Is it on? It is, yeah. It is. Maybe a little bit higher. Can you hear me now? Okay, all right. I don't know how to get this any higher, but perfect. Good. Okay. Is that better? All right. And I'm not going to talk about cats. So no dead cats, no live cats, no triggers. This is all interesting, but I found when I'm doing these talks that when you start talking about entanglement and superposition, you get completely sidelined by that because it's very mysterious, quite difficult to explain, and then you actually don't get onto the more important stuff. So what I'm going to focus on today is what quantum computers are expected to do over the next few years and why everybody's so excited about it. There's a lot of hype about quantum computing. Some of it is justified, some of it's not, and I'd like to talk you through that. So first of all, this is a quantum computer. I'm sure you've seen these before. It's a very odd looking thing. You've got a big silver cylinder in the middle of this thing, which is actually a dilution fridge. It keeps things there around colder than deep space, so literally about 2 or 3 millikelvin. And that's where all of the quantum activity happens. This is called Quantum System 1. And this was launched back in January 8th, 2019. And it was the world's first integrated quantum computing system. I was working for a startup competitor of IBM, and I was very jealous when they came up with this, because it's such a beautifully designed thing. Here is Another system, this is imaginatively called quantum system 2. This is something we're currently working on. Same thing, big dilution fridge in the middle, a lot of room temperature electronics around the outside. Now, the important thing about both of these systems are, as was said earlier, they're superconducting systems. These are computers, but they don't work anything like normal classical computers do. They don't have any transistors in them. They don't manipulate binary in the same way at all. They're not an incremental technology. They're not like GPUs or ML hardware that's using traditional classical hardware just in a different, more interesting way. This is fundamentally different from classical computers. They don't flip bits in order to do math. They use qubits, and I'll explain a little bit more about what a qubit is. A qubit, physically, is where you take a pair of electrons called the Cooper pair, and this, you'll have to strap in for this because this is ridiculously mind-blowing. You take the Cooper pair, you trap them in an electromagnetic field, freeze them down to deep space temperatures, and then once you trap them in something called the Josephson junction, you fire microwave pulses at them, and you get them to do very complicated math for you. So I'll come on to why that's important later. But that's ultimately what's going on inside a quantum computer. So, you with me so far? So we've got a bit on one side, and we have a qubit on the other. Now, a bit has two values. It can either be 1 or 0. And if you wire enough of them up and put some logic gates in them, you can get them to do arithmetic and add things up and all that stuff. The qubit is a very different thing, and it is a bit misleading. Often people describe qubits as being 1 and 0 at the same time. It's actually not that. It's a superposition, that is absolutely true, but it's a superposition of probability wave functions. The closest thing I can describe that is when you play two notes on a piano and you get a chord, that's a superposition of two sound waves. It's kind of the same thing. Now, you don't have to understand any of the stuff that's going on here, or what phi means, or what theta means, or anything. You just imagine, just for the sake of a useful visual mnemonic, that this qubit has it's like an empty sphere that can point to any surface of the sphere inside it. And by moving those two angles, you get that point to any place on the surface of the sphere. Those represent different values. Now, it's more complicated than that. The quantum physicists in the audience will kill me for saying this, but ultimately, it's much richer information than a qubit. Just by moving those two angles, you get a lot richer information. And as was said earlier, when you start connecting qubits together, you start entangling them, you create this vast computational space. And in that space, you can fit very, very large problems. And with clever quantum algorithms, you can come up with great answers very, very quickly. So, why all the excitement? Well, the excitement is that quantum computing power scales exponentially with qubits. Now, again, this isn't 100% true, but I'm simplifying, so again, quantum physicists will kill me for saying this, but that's kind of how it is. So, for every qubit you add to a quantum computer, if you want to match it with a classical computer, you have to double the classical computation in order to keep up with it. So if you want to simulate 10 qubits on a classical computer, you can do that on a Commodore 64 from like 1983. I used to have one when I was 13. It's like 64K of memory. You can simulate 10 qubits on a Commodore 64. If you add one more qubit to that, 11 qubits, you need 2 Commodore 64s to simulate that. And 12, you need 4, and so on. So you can see, by adding qubits to a quantum computer, you are increasing the computational power system exponentially. You get to 30 qubits, you'll need an AWS M4 instance in order to simulate that. That's a fairly hefty piece of hardware. Once you get up to 48 qubits, there isn't a supercomputer on the planet that can actually simulate 48 qubits properly. And once you get up to 60 qubits, this is completely in science fiction. But if you could somehow contrive to connect every computer on the planet together and then somehow meld all of them RAM together and add it on one machine and then run a simulation, you can simulate 60 qubits. So that's the reason that people are excited about this technology. Potential is there. Now, how many qubits do you think we're playing with at the moment? We had 65 qubits in 2020, 127 in 2021. And now, 4 months ago, I was on stage launching with my boss, Jay Gambetta, and others, 433 qubits. So we are way out of the realm of anything that could be simulated classically on any computer. That doesn't mean it's more powerful, it just means that we can't simulate it. So here's the potential. Quantum computing can never replace classical computers. You're never going to have a quantum computer on your lap. Actually, it's a 2 millikelvin, so I wouldn't suggest you do. But we're not going to see them replace all classical computers at all. What we're going to see is in a couple of, first of all, it will enhance classical computing. And secondly, there are very few specific areas where the applications or areas are. So for these very few areas, there's an exponential or polynomial speed up. In other words, there's a few places where quantum computing can play incredibly well. So it's a really odd situation where computation ability has taken a massive step up, or will do very, very soon. And we're starting to think about problems that we didn't even see as problems. I mean, most of the scientists I work with, they said, we never thought in a million years. In a million years, you'd be able to do prime factorization. That's, in fact, why we based encryption around it, because it was so difficult to do. We didn't think in a million years we'd be able to do molecular simulation. And now it looks like we actually might be able to do that at some point. So we're starting to think about problems we didn't even see as problems, just things we'd just never been able to do. So I'm going to talk about the potential, then I'm going to talk about the challenges, so that brings us back down to earth again. But quantum computing is focused on 3 main areas. First one is simulating nature. We're not very good at molecular simulations. Before I got into this field, I was assuming that we simulate molecules all the time. And we do, but they're very, very dumbed down models because they have to go the classical computer. So molecular simulation gets really difficult really quickly. In fact, we can only simulate molecules as complicated as caffeine, and barely that. So because of the electron shells in atoms of molecules, when they collide, they create more molecules, and these collide and create more molecules. You get this knock-on effect, and before you know it, you've got a problem that's too complicated for any computer to figure out. Quantum computers are very good at simulating nature. The second thing is data with structure. So I talked about Shor's algorithm and factoring. There's some great work that's been done recently about the acceleration of ML through quantum computing and ranking in symmetrical groups. These all sound very abstract, but we'll get on to how these actually apply commercially. And the third are search and optimization. Now, I put polynomial next to this. And what that means is there is advantage to be had there. It's not going to be as efficient as simulating nature or data with structure, but there's tremendous interest in search, unstructured search, optimizations like portfolio optimizations, and risk analysis. We're seeing quadratic speed ups, so square root speed ups in speed, but not exponential. Again, you with me so far? Any questions? Okay, cool. So now we'll talk about the challenges, and these are the significant challenges to this. The first one is noise. Electrons are very mischievous and very difficult to control. And so noise in the system becomes a perennial problem. Basically, after a gate depth of about 20, so after you've applied 20 gates to a qubit, the noise is so bad you literally get garbage here. So working on noise and trying to reduce the noise out of the system is something that we've had great success in. We're working hard on it, but that's a big problem. The second one is coherence. The electrons keep their states for relatively short periods of time, and then they decide to go and do something else. So what we're going to do is try and keep those qubit pairs in a coherent state as long as possible to do our calculations. The third one is making enough qubits. Up until quite recently, people thought past 1,000 qubits it's going to be impossible to actually fabricate that. About 6 months ago, we had a breakthrough, and I think we figured out how to get to 100,000 now. I'll share that with you later. And then finally, adoption. And this is much more of a design issue. But if you think about it, classical computing started off with logic gates 60 years ago. And it's taken 60 years to get to the point where you've got a containerized cloud-based service that you can just jump into and do an environment and just start. Okay. So it's taken 60 years to get it. With quantum computing, we had gates 2 years ago. We got to get to that place in about 5 years. So our acceleration is much higher in terms of making it usable by everyday, mainstream developers. We need quantum computing to be able to be used by lots and lots of people, and quantum computing is not easy. So making it compatible with the way people already work is a good fact. So here's the thing, quantum computing is currently exploratory. There isn't a quantum computer on the planet right now that can actually do anything that a classical computer can do, but we're very, very close to that inset date. So even though we're 2 to 5 years away from useful quantum computing, we already have 200 clients and partners who are starting this initiative with us because they know that in 2 to 5 years, everything changes and they want to be ready for that. So, we don't have a huge amount of problem getting clients. It's not a difficult sell. We have over 30 quantum innovation centers. We have 7 national computation centers. In other words, clients that we have our hardware on their system or on their site. So Germany, Japan, Korea, the Cleveland Clinic in the US all have their own dedicated systems. So even though quantum computing is not useful yet, it's been taken very, very seriously. So let's talk about some of those industries and some of the sectors. So the main ones we're talking about, first of all, actually, let me start with, you've got the 3 areas: simulating nature, complex structures, and search and optimization. Now, how do those split out into verticals? Aerospace and automotive are very interested in simulating nature and exploring different materials. Financial services are very interested in fraud detection, very interested in portfolio optimization. High tech, which is really the chemical industry, very interested in all sorts of things: supply chain planning, manufacturing. Energy, we do a lot of work with Exxon. I mean, I'll share some work we do with them later. Environment, utilities, again, very interested in optimizations. Huge amount of work in battery design as well. And then finally, healthcare and life sciences, probably going to be the area that we touched the first with quantum computing. If you think how much time and energy is spent in the scientific process of having to do wet trials and so on. Drugs take, I think, on average 12 years to get to market. If we could start simulating drugs, we could get to market a lot faster and save a lot more money. So they're very interested in it. So in terms of clients we're working with now, I don't want this to sound too IBM-centric, but it just happens to be the company I'm working for. So, we're currently working with these clients and many more, but JSR is a large Japanese conglomerate. We're doing some interesting work with semiconductor fabrication. Goldman Sachs, Boeing, JP Morgan, BP, ExxonMobil, HPC. So representatives of all of those different companies. And in terms of the value, this was a study done by our friends at BCG. These are not small numbers. So aerospace and automotive, the automated vehicle, flight optimization, fluid dynamics, we're talking $30 to $50 billion in terms of the values of those categories. Financial services, portfolio optimization, I didn't know this until I started. At the end of the day, banks run all of their trades through massive amounts of ML resources to do portfolio optimization and balancing. That A, costs a lot of money, and B, the energy costs are enormous. And they run for hours and hours. Quantum computers use a fraction of the energy to do potentially the same calculation. So interesting from all sorts of reasons there. High-tech industry, again, you're looking at $20 to $30 billion industry. Energy, solar conversions, battery design is huge. Battery design actually affects all of these. And then finally, healthcare and service, healthcare and life sciences. Projection is a $40 to $80 billion category. That doesn't mean that quantum computing is going to be worth that, but it means that we can become an important part of all of those categories. So, conservative estimate from BCG is that quantum computing has a potential to reach a value of about $500 billion when it comes to maturity. That's the kicker when it comes to maturity. We can't tell you exactly when that's going to happen. So what I wanted to do is just share with you a couple of videos. Apologies, these are kind of half commercials, half informative, because target audience for these is C-suite executives at Fortune 500 companies. But these dig a little deeper into a couple of the clients, JSR and Exxon. So I just wanted to play this for you. So that's the work we do with JSR. I've got another video I'd just like to share with you, which is some of the work we did with Exxon. You'll notice we actually did this video last year before we launched the Osprey chip, so it's actually got a previous chip in there, but I'll share this with you too. This is an optimization example. Thank you. So any questions on this so far? No? Good. Right, so I'll just go on to the next slide. So I've been working for IBM for a few years, so I'm not here to sell IBM to you, but most people agree that IBM right now are leading in quantum computing. So the question I often get is, why IBM? I mean, most people's idea of IBM is a company that was very, very big a while ago, with a lot of people wearing suits, you know, in the 1960s, standing next to large metal boxes. Why IBM? Why is IBM killing quantum computing? Well, IBM's got a very, very advanced research division. IBM Research has held the most number of patents filed by an organization for the last 29 years in succession. So there's a huge amount of hard tech, semiconductor fabrication and AI expertise in the building. And they happen to have a world-class quantum information theory team, the famous physicist called Charlie Bennett, who's been part of IBM Research. And basically a 100-year history of bringing technology to businesses. And I think the biggest one, I'm being slightly funny here, but IBM is not a startup. You can't do quantum computing as a startup. I've worked for a quantum startup. It's extremely difficult because of the capital intensity of the kind of work you're doing. You have to have an awful lot of fabrication facilities. You need to be able to make semiconductors. You can't do that, through the usual Silicon Valley VC type route. It's very, very challenging. So for all of those reasons, IBM are currently leading quantum computing, although the competition is fierce. So just quickly, we have 22 operational systems and many more on the way. Now we have 475,000 users, 210 members of our network, so 210 clients, 280 universities. We're running about 4 billion executions a day. And the aim here, we do a lot of work with national governments as well as just large clients. Our aim is to actually create an industry, not business. We're going to create a business anyway, but the industry is the important part. So we try to collaborate as much as possible, even with organizations that would be competitors. We do it in 4 or 5 different ways. The first one is we have a set of working groups that really advance the theory behind quantum. The second is the Quantum Innovation Center. So we work with clients and we encourage them to have clients so that they go off and help educate industry adoption. So we go work with clients direct. Services integration, we're working with a lot of ISVs, software vendors, to incorporate quantum into what they're building already. And then finally, Quantum Safe, which is our product to help protect businesses against we have a big education and workforce enablement. Part of this is making sure that people can use quantum computers and that we have enough of the workforce to actually support us going forward. And then, how are we for time? We've got another couple of minutes.
We've got a couple of minutes and then let's 3 more minutes.
All right. I'll skip over the development roadmap. This is our plan for the future. This has really been the organizing thought behind the entire business in terms of how we're planning to build bigger and bigger systems. What's good about this roadmap, I was very involved in this, is that every year we've ticked off exactly what we said we were going to do. And so year after year, we keep showing progress and we keep showing that they're not hyping and not exaggerating. The slow, steady progress is really good. I say slow, it's not really slow. I'll skip past this slide and I'll skip past multi-cloud workflows. What we're working towards ultimately in the next 3 to 5 years is a quantum-centric supercomputing model where we have quantum computing, classical computing, and AI and ML working together and orchestrating together to solve problems. And I wanted to just share this last video with you, which shows our vision for this. We're launching this system in November this year, and see what you think. So this system was designed to be modular, meaning that you can take quantum system 2, plug it into another one, double quantum computation power in the system. So that's been a challenge for industrial design. So here we have a 4,000 qubit system. And then by plugging 2 systems together, we can make them 8,316 qubits. And then the 3 systems, 16,662. That's why we created the hexagonal bridges, so that you can modularize. So we'll be unveiling this in November this year. Thank you. That's it.
Fascinating. May I ask you to come over? I give you a chair here. We go on a little improvised. I can't like moving chairs around. So, very, very fascinating. Can I give you one of those? One thing which struck me most here is actually, if you think about the complexity of people finding applications, and we looked at those typical things over the last week, like blockchain or AI or like many of those type of terms, and we always come back to the okay, but how do we bring it to life? How do we actually implement it? You have the X in your title.
Yeah.
How do how do you deal with something which is so complex that you actually, even explaining the bit, you kind of saying, okay, I think about the sphere, it's wrong, but just take the sphere. How do you simplify something like this so that a user can actually use it?
That's a good question. Most people don't know how their iPhone works. Most people, I mean, I've got, I think, 5 billion transistors in my MacBook Pro over there. I don't care at this point. I just use the software. And you have to be comfortable doing that with quantum mechanics, of course you do. So part of it is being bold enough to realize that you don't need to know or understand everything in order to move forward. Now, when you start with a nascent technology like quantum computing, everybody needs to understand it at first. So all of the people involved right from day one, like Jane, Jerry, the guys I work with every day. I say guys, people. Within a few years, other layers of people come in who necessarily don't understand the quantum mechanics, quantum physics of it. You get this slow abstraction. And in the same way that people don't think about the logic gates of the computers, the classical computers they're using, I said to Jane, we'll know when quantum computing has finally arrived, when nobody knows whether they're using a quantum computer or not. And so, honestly, our job is to try and make the technology disappear. So one of my challenges on the industrial design side, obviously, that's one challenge. But the challenge on the software side is to make quantum computers work in the way that the world already works. Like, we've succeeded when there's an API that you sign up for, you define your problem, you don't care about the solution, you just define the problem, send it off, and it returns an answer. Then we've succeeded with quantum computing. So, yeah. Does that answer your question?
Kind of. How do you do it?
How do you do it?
I mean, I totally get it, but this is actually for like when we think about like those young executives go out in the world, what would they what would they do? How could they contribute here? Because that is probably one of those. They're not the design experts to think about qubit designs.
Yeah.
They are not the some of them are CS engineers. They're not thinking about quantum computing as such.
Sure.
But how do I bring this to the world so that it becomes applicable?
Right, yeah. So any technology is, part of it is you're creating something that people haven't used before, it'll solve some problem for a user. Then you have to understand the user so well that you can make that technology fit into their life. And that is the most important thing. So right now, we're spending a lot of time understanding how mainstream developers work. Now, mainstream developers are not using quantum computing yet. They don't want to use it. It doesn't work yet. But we want to understand how mainstream developers think so that when quantum computing is useful, we can plug directly into their behaviors in their lives. So for instance, most mainstream developers, when quantum computing becomes useful, the first thing they do is they come to a site, they look at the docs. If the docs aren't well done, or well created, they will just leave. If you don't have code snippets on your front page, they will just look at you, they will leave. Developers, generally speaking, are one of the hardest customers or consumers to work with and the best advocates. They're terrible from a customer viewpoint. They hang around the top of the funnel, they don't commit, they want a lot of free stuff. They're very, very judgmental. But if they like you and you create a good enough tool for them, they will love you and tell everyone. And so understanding that, getting to the mind of your end user to the point where you can make your technology fit in with the way that they see the world is the trick.
This is actually pretty amazing. And let me do one quick replay from the two other areas where we had something very, very similar. Yesterday on the AR piece where they said, well, it is the developer who determines which AR platform will run because you need that ecosystem. And then on the robots piece where it was again, it's a closed garden approach for robots. It will be, if regulation breaks it open, it will become the ecosystem, the platform play where we have the developers. So for us actually to understand how software and hardware plays together is extremely important. And you can see in quantum computing, and I love this example, you have to think so much upfront because what if you have the fastest computer but nobody's writing code for it?
That's exactly our biggest nightmare is we create this fantastic hardware and nobody can use it. So IBM, before I joined there, made a couple of really good decisions. The first one was they open sourced Qiskit, which was the system, the very, very popular, most popular quantum software. Open sourced it, a very odd thing for IBM to do, and absolutely brilliant. So we've got a huge amount of adoption. Everybody uses it. And the other thing is we put real quantum hardware out for anyone to use for free. So again, it just drove the adoption. So we have large tranches of universities where people only know Qiskit. So Qiskit out in terms of adoption is 4 times that, I think, of CERN, which is the nearest competitor. So getting the software out there and allowing the open source, the magic of open source to happen. People start writing libraries, they start talking, communities get crazy. One of the things I didn't share is our roadmap. And the roadmap is smart because it shows our progression over time. But the really smart thing about it is that it understands as an ecosystem. There's a bunch of quantum physicists at this level writing pulse level software that feeds the next layer up, where people who don't understand that shit are creating software at a higher level, and then model developers even higher than that. And that is an understanding that there's an ecosystem at play and everybody benefits from the open source stuff.
Very cool. There was a question over here. Nice to meet you. I'm also an IBMer as well, so it's nice to see another one here. My question is about the scaling of quantum computing. So if you mentioned that 60 qubits is equivalent to the entire world, like, why do you want to scale it up so you have so many qubits in this machine? And like, are there specific use cases associated with the milestones you're setting for those?
Yeah, so the first question is, and it's probably, I need to clarify that when I present this. So those 60 qubits we're talking about were logical qubits, meaning they function perfectly. And it was talking about what classical computer you need to simulate those. It's not the same as doing useful work. So the challenge we have in the 433 qubits we have is they're good qubits and they've got high fidelity, but they're not logical, they're not perfect yet. So we still have a ways to go. We need to create 40,000 to 100,000 qubit systems before we can do the kind of work that we're really excited about. So what's interesting about the way quantum computing, the problem a lot of people have with Google's claim of quantum supremacy was it didn't do anything actually that useful, it was just random number generation. And the second thing is that there's not going to be a point in time where suddenly, like, oh my goodness, a quantum computer can now do everything a classical computer can do. They've gone from being not useful to marginally useful in a few areas to increasingly useful over time. So it's like a slow continuum. And I can't give you a qubit count or a time in the future when that will happen. We reasonably expect it between 2 to 5 years. And a lot of people are expecting material science to be the first area that gets the advantages of quantum. So low-level molecular simulation of not things like proteins, which are very complicated, but molecular simulation for materials, and then ML and ML's acceleration. But I couldn't give you a date. So that's your question.
Maybe to add to this, and because I have to be at Google at the same time in a very close team as we announced the quantum supremacy.
Yes.
It was, well, you even use the word, right? It's kind of David talked about the platform, talked about the smart move of actually bringing out the code. This is a typical PM move, right? So to prepare your users. Another typical PM move, what Google did, is they kind of like coined a term. It felt like this didn't come out of a blue sky. It was well prepared that we wanted to place the quantum supremacy call, and we kind of like briefed the newspapers and we got it out there. So it was actually very, very good piece of advertisement. So if you don't have a tool set to share, you kind of just make it up.
Well, yeah, John Prescott coined the term quantum supremacy. And
exactly.
Google were like, right, how do we claim that? And it was, it was smart.
Yeah.
It worked. It worked.
There is a question up front here.
Right?
Oh, sure. No, first here.
Oh, I'm sorry. No,
Okay. So I have a very basic question. So you have been in the creation space and you have worked for some of the biggest companies like Google for over 20 years. What drove you into quantum computing, into such a niche space that was not proven in 2018, 2019? Like, what expectance did you have out of it?
That's an interesting question. I got into it when I was at King's. One of my professors talked about a paper that had been written by Feynman and said, look, it would never happen in your lifetime. This was 30 years ago, so I can't believe it. But, you know, Moore's law is going to hit a dead end at some point. Quantum looks interesting. Didn't think anything of it. And then I think it was at Google when Helen Evans started talking about quantum computing. And then when I think I hit 40 and I decided I really wanted to understand quantum mechanics. It was on my bucket list. No, I don't understand quantum mechanics. But I gave it a college try. I tried hard and you know, I learned enough to be dangerous. And that got me into quantum, and then I got the bug, and then I decided I wanted to work in quantum computing.
On a follow-up to that, you mentioned, I thought I saw 22 operational systems on this slide.
Yes.
Is that 22 quantum computers, 22 buildings running?
Sorry, 22 quantum computers. So quantum system 1, which is the original system, we have 22 of those.
So, how many will the world need? You know, we said this at the beginning with, you know, nobody will need computers, and look at us now. Will it be like cloud computing, where there's 5 to 10 big vendors in the world, IBM, Google, Alibaba, Tencent, that run the world's quantum environment for us? How will this evolve as we do?
It's a really good question. I honestly don't know. They're expensive, so you're not going to get a quantum computer on your lap unless something very sort of crazy breakthrough happens. It's going to be data center, warehouse center, cloud will be the model. I think there'll be a hardware advantage for about 5 to 10 years, and then the hardware advantage will IBM. Yeah, or for whoever leads. Hardware, obviously, you can't differentiate them for that long before everybody else catches up. Software is a different thing. The error correction is done in software, and that might actually be a black box that people can actually own and leverage. But I think we'll probably end up with hyperscalers getting involved and becoming the distribution for hardware. The magic is in the software. That's the interesting thing. Is the hardware looks impressive and is beautiful and it's fantastic chandeliers. But Qiskit Runtime, which is the software that we've developed, that's where the orchestration happens. That's the really hard part. And so that's why I'm hedging my bets a bit, saying it might not be just a hyperscaler play where, you know, the big people win.
I want to point out one more thing. This is actually has nothing to do with quantum computing. Very often, like it happens to JB, it happens to me, students come to us and saying like, what should we do in life, and how do we become successful, rich and sexy, and so on and so forth. And you know, we have our chats. Now, we see like with growing age, you meet extremely successful people like yourself. And he said something which I think is very common for successful people. As I was 40, I just wanted to learn how quantum computing works. For you guys, you come to Cornell every day. Like this is, you paid for this stuff, right? You are here, it's clear that you are learning. But I bet you, a few years out, you are in your treadmill, you're doing your job, you have family, you have whatever. Please remember him, that he kind of says, I wanted to learn this and I learned it. This is a sign of not only like a successful person, but somebody who is steering his life. And sorry, it has nothing to do with quantum computing, but I thought it was such a brilliant, beautiful lead. And like, remember him in 5 years time.
I'll take the flash rate, thank you.
So when I was doing my research in quantum computing, and I tried to use it myself, I tried doing Shor's algorithm on it and so forth. I see a lot of the applications are usually B2B, right? So these Monte Carlo simulations for financial risk, or you know, molecule simulations of drug discovery, etc. Like, do you see quantum entering more of the B2C space in the future, where consumers, like any regular person, perhaps it's like you said, abstracted enough, but where do you see like consumers, perhaps other than from a business perspective, being able to use this, and perhaps what problems that consumers might face would solve that? If you were to guess.
That's a really good question, which is usually a way of saying, my God, I couldn't answer that. I think it's always really surprising when B2C rears its head. So, you know, I mean, the history of computation is that. Nobody thought there'd be personal computers. mean, that was insane. And the same with ML we're seeing now. I mean, who would have thought ChatGPT would just blow up like that? Or Midjourney or any of those fantastic services. AI was B2B. So honestly, I don't know. I know that there's things that quantum is quite good at that could potentially have a direct-to-consumer angle to them. I think they'll emerge after B2B has done its work. I think, but I couldn't answer that.
And by the way, on that, I added it real quick on that slide. You had financial services and banking as the highest value if you added them all up for value benefit. Is the financial services industry going to drive this development?
I don't think so. I think that's BCG looking, long term over the next 10 years. I think the first industry that we get involved with is probably going to drive the rest. And what's interesting about the financial examples and those optimizations like Monte Carlo is they require a lot more hardware and a lot more higher qubit count than things like molecular simulation. So I think, again, this could change tomorrow if we have a breakthrough, but I think molecular simulation, material science, everyone's very excited about the idea of being able to sequester carbon out of the atmosphere and things like that. That's, to many people, the first step. And then financial services will come after that. Yeah.
Actually, one question, follow-up question to this before we move on to the next, is you had Cleveland Clinic. You had governments, you had states, you had Quebec, not quite yet a state, they wish to over, and then you had Cleveland Clinic.
Yes.
Wow.
Well, Cleveland Clinic are really good at medical research. And they are very forward-thinking, and they're doing a lot of work around the acceleration of the scientific method. So applying ML and AI to scanning through scientific papers and then basically accelerating the scientific method itself. For that, you need a quantum computer. So they're very ahead of the game. They have a quantum system 1 being installed right now. We're doing the ribbon cutting on that in a couple of months, and they've already signed up for a quantum system too. So yeah, Cleveland Clinic, they're a phenomenal institution.
So, just to say, if we think about applications, right? The whole thing about drug development or medication development, we could, at the moment, there are companies, there are startups who are trying to use AI to test out different molecule combinations, billions of it, but they don't know how to test it on a human, right? So they make kind of estimations. This is where quantum computing can help, that they actually, you generate something, and now you're saying, I want to have a simulation, how would this look in a human? Like at the moment, we have very rough tools, and then we put it in mice, and we think mice are like humans, and then when the mice survives, then we say, okay, then let's try the more mice, so then actually at some point in time, it goes to a human, and then it goes even more. Yeah. Next question.
Oh, sorry.
Thank you so much for coming. So I had a question about, you said earlier there's a lot happening in software, but not so much happening in hardware. So the first time...
I didn't, if I came across that way, I didn't mean it. There's lots happening in hardware and software.
Yeah, so I have a question about hardware. So the first time I heard about quantum computing was 2016, and I saw actually in the video for the first time that you're aggregating the machines together to increase the capacity. Is that correct?
We are now. That's the plan for the next system that's launching in November. Correct.
And so my question is, for my understanding, what's happening in the machine is that the conductors are made of graphene. And do you see there's, improvement on the conductor side to make the computational power more improved in the future?
All right. Yeah. So the breakthrough that happened last year, we have a scaling problem. We couldn't get past 1,000 qubits because you put 1,000 qubits on a chip, and then when you cool the system down, the chip breaks. Literally, we have to deal with fabrication problems like that. So then some scientists were playing around like they do with smaller chips and realized that we could connect smaller chips using quantum interconnect. And that solved 5 problems. The biggest one was that the chips didn't show. The second thing we realized that then we could actually create by putting 3 or 4 different chips in different chandeliers, freezing them, we can connect them together using long-range couplers. So suddenly, the chip is as big as the amount of connection that we have between the systems. So the modularity of the design, the industrial design, really came out of this breakthrough we had where we realized that we could connect chips together and have them function as one large chip.
So I've read that there's a risk of data theft for organizations who are not ready to transition cryptography to post-quantum algorithms.
Yes.
And you also mentioned that quantum computing will not replace classical computing. Isn't this a risk for organizations like financial services? What can be done to combat this?
Yeah, it's a really good point. So 3 years ago, quantum computing was a question of, is it going to happen? And not when. And then about a year ago, everyone was like, no, it's completely when. It's definitely going to happen. It's not a question of if. It's clearly going to happen. The moment that happens, then it's like, okay, how long is it going to be before somebody runs Shor's algorithm properly and breaks up to 20 encryption? 2-3 years ago, people were saying 20 years, 30 years. Now, conservatively, 5 to 10. That's not that long. And the biggest danger with quantum computing is the harvest now, decrypt later issue, which is because nobody ever thought you would ever be able to do prime factorization, we've been happily sending encrypted data to each other in plain view, easily recordable, because we didn't think it would possibly break it. So we've been sitting on treasure troves of data for decades, and suddenly it looks like somebody's going to come along and decrypt it all. So half of the business at IBM Quantum is quantum computing. The other half, which I didn't talk about, is quantum safe. And that's a little, it's more of a consultancy business, but basically we're working with clients saying, we understand quantum computing better than anyone. You kind of need to start protecting yourself now. So it's a long involved consultancy process, but ultimately you use cryptographic scanners to go through IT infrastructures, take out anything that basically uses prime factorization or can be attacked by a computer. And then we've been working with NIST, 3 of the 4 quantum safe cryptographic methods are actually IBM inventions. So, part of our job is to make the world quantum safe as well.
So hold on, what you're saying is if I start a business and just saving encrypted data in order to sell it tomorrow, that will be a business case?
Sadly, yes. But yes, you're right. Somebody joked that we're making the gun and also selling the bulletproof vest at the same time.
Other questions from the audience?
Thank you. So you mentioned about the ecosystem and how venture capitals or startups are still not in the ecosystem. When or where do you think that venture capitals or startups would add value to the industry that you will be building?
Oh, okay.
It's just that my company, they used to, a couple of years ago, we had to the other team invested in Zapata computing, and
yeah,
because we weren't sure of what we're doing. But
yeah,
how do you position venture capitals or startups?
So I didn't mean to say that venture capital is not important to quantum peers. I was talking within full stack quantum offerings. So if you make the hardware, make the compilers, make the system, do everything, that's very hard to do in a classic kind of Silicon Valley VC because it's so capital intensive. But there are many excellent quantum startups, Zapata being one, Xanadu, lots of companies that are focusing on software and algorithm development a lot of the time. Another one is StrangeWorks. So there's an ecosystem of startups. A lot of them are focusing on individual verticals, like good chemistry. They're like, okay, we're going to just do chemistry really well with quantum. We work with different hardware vendors. So that side is still going strong. Obviously, there's a downturn, so VC investment for most things has probably dropped off a cliff, and for quantum it has. But we at IBM Quantum, we love startups because they're a great way for us to get more clients. So yeah, no, it's a full stack offering would be very, very difficult to be VC funded. I worked for a VC funded full stack, and it was a real struggle. That was Rigetti. We made our own chips, and it was very difficult to fabricate those.
I would have one more question. So we some of the students we talked about GANs, the AI tool where the computer two computers compete against each other essentially as a reinforced learning method, general adversarial networks in the deep learning space. That is obviously not like AI is in this case limited, not anymore by data, but by computational power. What are all, and I normally don't engage in this kind of dialogue, but I'm actually curious what you think. Like there's people saying, oh my God, the question is not whether we will get AGI, artificial general intelligence, it's only the question when. Is that a topic which is even touching the quantum computing area?
Yes. Yes, it is, but tangentially. So right now we're very interested in foundational models. IBM has been investigating those for a number of years. And we're very interested in the interplay between quantum and how it can potentially accelerate ML. That's all I can say. But yeah, there's interest there, definitely. We proved on the quantum ML side, things like kernel alignment has been seen to be accelerated by quantum methods. So it's interesting.
And then, but just like all the stuff which we know today, if you start running those, like if data is not a restriction, right? You have those two restrictions. You have data and you have computational power. The whole deep learning side of GANs reduce the data needs. So it's only computational power, and you guys will lift that one. So that means we are up for a journey.
Yeah.
There's one more question.
No, we just wanted to thank you on behalf of Cornell for coming.
Oh, thank you.
And amazing.
Thank you.
Hello everyone, I am Team 6, speaking on autonomous vehicles and machinery. Any sufficient advanced technology is equivalent to magic. A quote by Sir Arthur Clarke, a science fiction writer, science writer, inventor and futurist. And speaking of sci-fi, just by taking a close look at the evolution of vehicles through our sci-fi screens, we recognize that a lot of these ideas have been around for decades. The almost supernatural self-driving cars in the swinging 60s, think of the Love Bug, to the Batmobile, to tactical response vehicles, if you've ever seen Time Cop, flying taxis, which was truly the golden age of sci-fi cars. And also in more recent times, the more grounded sci-fi concept cars, we see a trend of product placement by automobile makers such as Audi and Lexus, who have sort of combined this autonomous vehicle concepts with a lot of the futuristic cars in movies. We've always been fascinated and also weary of self-driving vehicles. 3 out of 4 people do not trust self-driving vehicles. And surveys show the top concerns were safety, control, those who prefer to drive for pleasure, and those who just don't understand the technology. But as we know, much of these concepts have been around for centuries. Da Vinci designed the car that could move without being pushed or pulled. Whitehead's invention of the torpedo that could propel itself underwater was groundbreaking. So also was the Stanford car. The idea of a remote-controlled lunar car also proved groundbreaking. Tsukuba's autonomous passenger vehicle was able to recognize road markings moving at nearly 20 miles per hour. And then fast forward to 2004, up until about 2013, DARPA sponsored a series of challenges that also pushed automation and autonomous technology forward. By 2015, Tesla's autopilot arrived. And come 2016, Uber announced level 3 autonomous vehicle testing in Pittsburgh. That same year, we saw the first autonomous freight delivery by Otto in Colorado from brewery to distribution center. By June 2017, 11 of the top automakers announced a timeline of AV to market by 2021. Ambitious. But not long after, Waymo, as we know, now owned by Google, announced in Arizona that they were performing level 4 automation testing. Come January 2018, GM Motors put in a permit to build cars without steering wheels, as well as pedals. Waymo purchased a lot of these vehicles. And today, in San Francisco, Waymo employees have access to these vehicles, boasting running level 5 automation in trials. Now, in terms of the technology, there are 6 levels of automation. 0 being zero automation, 1 known as driver assistance. In this case, the driver is hands-on. 2 being partial automation, hands-off. Conditional automation, eyes-off. High automation, mind-off, where you could just sit in the car, do something else, be more productive. And then full automation, think about vehicles driving around with no one in them. Or better yet, vehicles making school runs to pick up and drop off kids. Now, some of this tech has been around for years, from the inexpensive, frequently used cameras, GPS systems, maps, inertial navigation systems for velocity, cruise control, T to cruise, sensors, both ultrasonic for short distance data, as well as infrared detection for pedestrians, road markings, and so on. And then also the expensive tech. We looked at some of them like LIDAR, light detection and ranging, radar, as we know of. But also coupled with all this tech is the software. Coupled with all the hardware is the software, the machine learning algorithms, computer vision, supervised learning, deep reinforcement learning, providing foresight and hindsight, and making all of this happen. With a quick look at the impact. The US annual vehicular fatality rate is 38,824. And 94% of crashes are due to human error. Within AV is the potential to reduce crashes by 90%, and also saving approximately 190 billion per year. Other benefits include improved safety, public health, increased productivity, quality of life, mobility and accessibility. Think of the elderly in our community, those with disabilities. But also with these benefits comes costs and problems, potential problems. Increasing congestion, urban sprawl, and social inequality issues. Think back to the impact of building motorways, highways through our cities. The issue of autonomous vehicles is not entirely just a tech problem. but it's also about planning, what it means to our cities, what it means to society at large. Another of my favorite quotes: the price of excellence is eternal vigilance, if anyone has seen Better Call Saul. But also in the forecast, we show that the global autonomous vehicle market has a potential to be worth $615 billion by 2026. Unfortunately, our speaker is not here yet. So at this point, I will close the introduction. Thank you.
Hey guys, can you hear me?
All right.
Perfect.
Without further ado,
Sweet. Good timing.
yeah, I'll introduce our guest speaker. He is Program Manager of Autonomous Systems at Microsoft, building and scaling autonomous systems and platforms with world's foremost AI, autonomy, and R&D teams. He has 2 decades of multidisciplinary experience in building 0 to 1 and growing 1 to N production systems. He has a passion for building innovation teams aimed at rapid market dominance. He has hands-on product development, engineering management, large-scale transformations, and product-lead partnerships in the world's largest enterprise. He did his master's at Chalmers University, MBA at Columbia Business School, and Masters of Software at Oxford. Without further ado, please help me welcome Fahad Khan.
Hey guys, can you hear me okay?
Perfect.
Yes. Yes.
Yes,
First
we
of all,
can.
my apologies. First of all, I'm excited for 2 reasons this week. One, that I'm speaking with you, and second, that I survived the chop. So that's to begin with. Are we still okay with the volume?
Yeah, we're good.
Okay, yeah. So it's my apologies. We've been packed back to back, working on a few important items throughout this week, and obviously a lot of anxiety across the tech world. Needless to say, at Microsoft also, it came as a surprise. With other companies, it was sort of kind of known, it was on the horizon, but for us, it was like totally surprising. And then the other problem is that I work on a West Coast timing, and I had my clock set at still 4 p.m. here, and I was all set, ready and steady for a commute to Roosevelt Island, and the traffic was terrible, so I decided to sort of join virtually. So my apologies for that, but I'm excited to be here. Now, what I want to talk to you about is 2 things, really. One is how Microsoft innovates, right? And then second is the project I work on. Before I begin, I want to sort of caveat that this is, given the sort of short time, I had to get the, to decide to join you guys in person. There wasn't enough time to get PR approvals for a recorded or broadcast, an official sort of Microsoft stand. So this is in personal capacity. I will sort of try to sway away from anything confidential, anything non-public. But anything I share would be, obviously, virtual NDA. So for the benefit of the class and for the benefit of the Cornell tech community. So kind of keep that as off the record, even if I inadvertently say something that's confidential. So that's without that.
We've emphasized to them to keep everything in the classroom, to stay in the classroom, that we are bringing in special speakers and they're getting privileged information. Don't tweet about it, don't share it. So we've made that very clear for all our students.
Thank you so much. Thank you. All right. So Microsoft's story is fascinating for me. As a kid, I always wanted to be either, a chief software architect of a company that I would found, or be a program manager at Microsoft. And it's been a long journey. I joined Microsoft 2 years ago from Amazon. Before that, I was at a global system integrator for less than 2 years, where I led a team of teams, about 150 people. Before that, during my Columbia days, I was recruited by David McClure as an MBA associate for the at that time the largest seed stage VC fund, 500 startups. And before that, about 10 years in New York City, entrepreneurship ecosystem with some satellite offices in Palo Alto and other places in the world. So I've been sort of in the rodeo initially, as an entrepreneur, and then as I got older, wanted to sort of really, see how large companies innovate. And really, at Columbia Business School, I really didn't learn anything but two things that I didn't know anything about. One was search funds, and other was corporate entrepreneurship. And that's when I decided that, if I want to do a startup, I'll probably do a startup unless I won't do a startup unless I have $100 million, or I just would want to just work for companies who can, put me in charge of $100 million. So that's my sort of journey. So I'll leave at that, let you ask questions of my sort of past experiences, during Q&A. Jump to my point number one, how Microsoft innovates. The official model that we use internally within so let me just explain, where do I sit and why do I know about how we innovate. I work for the TNR organization. It's a very small org where we report into the CEO of Microsoft, and we're under the office of CTO. Kevin Scott is the CTO of Microsoft, who came to Microsoft with the acquisition of LinkedIn. The entire MSR, which is Microsoft Research team, is under that org. So that's the core, the essence of the entire TNR. But we have some teams under some amazing long-term leaders who are focused on either specialist research areas, advising the office of CTO, advising the rest of the company, and also filling in the gap of two horizons, the Horizon 1 and 3, and I'll talk about that in a minute, and that's the framework we use. So we are focused on incubating new products. The executive that I work for, Gurdeep Paul, I had met him with Satya, I think in 2014-15. It was Satya's first appearance as a CEO of Microsoft at a conference. I happened to be there as a founder. I met him and one of his close friends and associates, who's my CVP today, Gurdeep Paul. He was the head of Skype, head of Bing, head of the team that is now known as Teams. So he leads the new product incubations for Microsoft. And the idea is that, while Microsoft Research for the past 3 decades or so has been focused on inventing or pushing the frontier in basic research, right? So we're probably one of the 2 or 3 largest research organizations focused on advancement of computer science and other technologies, in quest of the next big thing. But most of the research that we do is like 10 years out, 20 years out, and most of the Microsoft verticals or vertical businesses are focused on Horizon 1. So there was a need to bridge the gap where how do we commercialize technology that is invented at Microsoft Research, looking at 10 years out, but how do we commercialize that in near term, maybe 3 to 5 years, so Horizon 2. So we use that McKinsey framework of 3 horizons, Horizon 1, Horizon 2, Horizon 3, where you essentially set up an organization where Horizon 1 is focused on what works today, Horizon 3 is focused on inventing for the very long future, and Horizon 2 initiatives could kind of bridge the gap between the two. So that's our innovation model. That's how Microsoft innovates. Now, the project that I'm working on, autonomous systems, a little bit about that. And I have a couple of slides to show you in a bit. One of the things that we do at the TNR, Technology and Research Organization, is sort of create a worldview of what's disruptive as it relates to our business, as it relates to areas that Microsoft is going to play in, right? And we call it Disruptive Technology Review, DTR. That is something, Kevin Scott, his team puts together for the Microsoft leadership team, and they decide which areas we're going to invest in and how. Autonomous systems is one of those areas. And we started this autonomous systems group with the acquisition of a company called Bonsai, which was the first investment Microsoft M12 had made, a VC investment, which is a corporate CVC, a corporate VC arm of Microsoft. They work very closely with us as well, given our focus on Horizon 2 and looking out at Horizon 3 also. We acquired Bonsai, my CVP, my VP did, and then we also started incubating another project called AirSim. And I'll talk about that briefly and show you a couple of slides. So autonomous systems is key to us, one of the key sort of area where we're looking at. And the strategy, using public information I'll share with you, is that we've placed a lot of bets across autonomous systems, whether it's our $1 billion we put in Cruise in partnership with GM, whether it was a direct investment M12 made in Vertical Aerospace, which is a flying car company out of UK. They haven't flown the car yet, but they were an investment. Similarly, there were investments in Germany in another flying car company called Volocopter. And then so on and so forth. And there's many other projects that I can't talk about, undisclosed projects. But one project that I can talk about, and it's public, is AirSim. So let me talk about what autonomous systems do, right? So just to give you context, we feel that a lot of this autonomous car companies, I know there's some computer science kids here as well in the class. So while it's a lot of mechanical engineering, electrical engineering, computer science folks involved, a lot of the hardware that has to sort of act in the real world, the robot, so to speak. But a lot of the training of that robot is happening in simulation, right? So that sort of gave birth to simulation and modeling as a key area that we want to look at. Because historically, Microsoft has created tools for software engineers, whether it's our Visual Studio tools and other language technologies that we've been inventing for the past 30 years. We're looking at simulation and modeling also as an area where engineering workloads, not just software engineers, but what about other engineers like mechanical engineers, aerospace engineers, the tools they use, they'll be run off cloud too, and we want to be participant in that area. So that's another sort of area which is related to autonomous systems. So simulation is at the heart of a lot of these autonomous systems companies. To give you an example of Google, our friends at Google, they have at least 2 bets in autonomous system space where they're actually building everything end to end, Waymo and Wing. Wing is in the sort of drone delivery space, Waymo in the autonomous car space. So to give you the perspective, in the past 5 years, they've grown their simulation workloads to the point where 2% of all Google compute, I don't know if it's true or not, this is public information, I think they shared in one of their YouTube presentations. So 2% of all Google compute is being used by Waymo to run their autonomous cars in simulation virtually. So simulation is a key element of how autonomous systems are currently built. Whether it's efficient or not, I can't say. There are hurdles. It's not been. There's a gap scientists call sim to reality, sim to real gap. It's huge. There are a lot of research efforts across the world in some of the top universities focused on sort of bridging that sim to gap. Anyway, so how you do simulation is very important. So if you look at the history of simulation, the use of using 3D engines, 3D gaming engines, to create virtual worlds in which to sort of realistically represent robots, whether they're cars, planes, or indoor robots, really started with a research center in Barcelona, the Computer Vision Center. They created a simulator called Cynthia. That was probably one of the first efforts in using 3D simulations for AI synthesis. And it didn't take off well. Then in 2007 and 8, we invented AirSim. A team of 4 or 5 researchers at Microsoft Research published a paper, with that name, AirSim, and published their tools that they built to do simulation on GitHub. This was 2017. But let me give you the idea of how it came into being. We hired a guy, a good friend of ours, at Microsoft Research to fly drones for different teams. Multiple teams and multiple research teams at MSR were working on, working off of drone data collected via drones. So this guy's, his job was to just fly drones for different teams to gather data, right? That was his job. And one team wanted to sort of change that. They thought, hey, it is quite inefficient and nearly impossible if we need to collect data, let's say data of Seattle, drone flying over Seattle, and with domains, all the sort of domain, there's a concept called domain randomization, where what that really means is that can I get the data, the aerial data of or geospatial data of Seattle with every possible domain randomized, which means that time of day, different weather conditions, whether it's snowing, raining, etc. Can I gather all that data and use the data to train my algorithms, whether they're computer vision algorithms or other planning algorithms that a robot can use to either find path as to how to fly, or detect something, or inspect something, capture data, send it back to wherever it needs to send back to, so on and so forth, right? So they determined it's impossible to do that, but it is possible to represent a robot in simulation. And in near realistic sort of 3D environment, you can fly those drones and gather that data, and without too much of a loss in accuracy. So that's what they did. They published AirSim. Since then, it has become a revolution. It has become a central area in car space. So there are 2 industries vis-a-vis autonomous cars, not cars, but autonomous systems. There are many industries, but 3 major areas that I can talk to you about. One is obviously that you guys are aware of, the self-driving cars, right? So to say, the problem right now in self-driving cars is that every self-driving car company is reinventing their wheels. So will that work? Yeah, it doesn't seem like. So the tech stack each company has is being built from ground up, which means that nobody's using a same set of stack to do simulation synthesis. Waymo has its own. Cruise has its own. GM is using third-party tools. Ford is using third-party tools. Each of these traditional car companies have invested in different sort of, these simulation companies like Motive and, so on and so forth. And some of them have been shut down. For example, Argo was shut down by Ford recently as one of the top companies in this space. So that's the challenge autonomous cars have. However, there's a lot of investment and a lot of sort of growth that went into this area. So that's why we know, okay, autonomous cars, but there's a lot more to it. The second area is aerospace, which is flying cars. I'll talk to you about that particular one. And the third area is really tackling the control systems. The past 100 years of industrialization has been built on control theory and automated systems in factories, whether it's CPG companies creating chips and Pepsi and Coke and all that stuff, right? But there's need for it. So Bonsai is focused on that industrial autonomy. How do you sort of bring autonomy to already automated control systems? So that's a much deeper, much bigger, and much more complex a problem than cars and flying cars. We believe. So let me back up a little bit, just to give you an idea of the 2 industries. So the car, you can look up the real numbers, but the car industry is anywhere $3 to $4 trillion a year. Aerospace $600 to $800 billion a year. So obviously there's much less investment because the industry is smaller, and in cars, we've been fascinated by cars a lot more. So in the past 5 years, all these companies have grown up. And a lot of these workloads, spending tens of millions of dollars in different cloud companies doing simulation. So we thought that it is time is right for us to create a platform for aerial autonomy because nobody's focused on that. So that's the sort of project I work on, a project AirSim. I'll show you a couple of slides as to why that's important. And then yeah, I'll take a pause and ask let you guys ask questions. But let me just walk you through this, a couple of slides. Okay, let me know if you see my slides.
Yes, we see it now.
No, we don't.
Okay, great. So Project AirSim really is a simulation tool.
Hang on, I'll get it. We got it. Go ahead.
Okay, great, awesome. All right, so Project AirSim is one of our autonomous systems bet. I gave you the history of it, but what does it really do, right? So what are the challenges that are there, right? So, we're all familiar with this, right? This is going into Silicon Valley, or actually coming into San Francisco from Silicon Valley, right? And the reason I'm not there with you guys today is because, something like this on NJ Turnpike, and then a lot more worse stuff going into Lincoln Tunnel, coming out, going through the Midtown, then going into Queens, turning around, coming back to Roosevelt Island, and then walking maybe 20, 30 minutes from the parking garage to where you guys are today, right? So we don't have things that fly from any place to any place, right? So the go-between cities are these large infrastructure-heavy airports, right? That's pretty much, and it's a mess, right? And then, the aviation today is really monopolized by, two things, regulations set by folks like FAA, CAA, and these highly trained pilots. And the disruption is that these pilots are becoming increasingly in short numbers. Right. So this was the sort of urban air mobility concept developed by Dr. Shin, who was the associate administrator at NASA. So we work very closely with NASA, and I've hosted FAA and NASA jointly twice at our Silicon Valley Center to talk about how we enable, and we have some joint projects going on as well. And this was the sort of founding vision of AirSim, a virtual environment in which intelligent autonomous agents can experience the physical world in order to learn how to operate in a collaborative, safe, and accurate manner. Now, what AirSim is a AI-first simulation platform for training and validating autonomous aircrafts in high-fidelity simulation. On the left side, you see a simulated aircraft, flying over map of London. It's a near-realistic, not a geospecific. Actually, it's a geospecific map, but you could actually pick a geotypical map also. And those on the screen that you see is actually sensor. Those are real sensors. They'll probably act with high degree of similarity in a real aircraft. We have companies like, and I can only give you the ones that are public. So Bell Helicopters is using AirSim to develop their next, not EV, but VTOL, a vertical takeoff cargo plane for not commercial defense related scenario. I can't delve more into what that is, but I can delve into another company that we partner with. So Supernal, owned by Hyundai. So Dr. Shin, I mentioned the NASA administrator who conceived the idea of urban air mobility as sort of the future where we need to move to, so that the problems that humanity faces with those traffic jams, with those large infrastructure heavy airports, and so on and so forth. How can that be solved? Was his vision. He is now the president of Hyundai Motors, Urban Air Mobility Division, and CEO of Supernal, which is a wholly owned flying car company, based in the US for Hyundai. They're using AirSim to build their aircraft, doing a lot of validation and testing, but also product development in simulation. I can talk a little bit more about that, but this is like a rough roadmap as to what we're building, where we're getting to. This is the overall sort of focus we have right now in the outdoors. Inspection scenarios are very big on us. Similarly, drone delivery, as well as the aerospace, the neo aerospace, where traditional and new aerospace companies are building these flying cars or vertical takeoff vehicles that don't require airports, but rather potentially can take you from point A to point B. And that's an area that's very of deep interest to us. Now, before I sort of end here, the reason for us to create Project AirSim as a commercial platform after having open sourced the early version 5 years ago is as follows. Number one, we didn't see a lot of input going into the open source project. Most of the contribution was being done by us, and the open source project is being used by over 3,000 organizations. So every Air Force organization in the world, U.S. Air Force, Israeli Air Force, everyone uses AirSim. Companies like Amazon, Google, so on and so forth. And this is public information. You can actually check it out on GitHub. They utilize the open source version of it, but none were sort of contributing to it. And since we, announced the launch of our commercial platform, our sort of business has grown 10x in less than 1.5 years. I just looking at numbers. So we're essentially a startup within Microsoft, and the growth we have seen since sort of announcing and launching the commercial platform, we really think that the world is onto something. So yeah, I think that's Project AirSim. That's what I work on every day, and hopefully we'll continue to. One quick thing. Don't take a screenshot, but that's the sort of area where we are focused on, where different verticals, the core product that we're building, but what are these sort of areas? eVTOLs and aerospace is big, what I focus on, and there's a lot of stuff that goes on in defense. We have some collaboration with DARPA and U.S. Air Force, so on and so forth. And it's a very exciting space to be at. Last point I want to say, Microsoft will never build cars or aircrafts, but the reason this research project and now this commercial startup that we have within Autonomous Systems Group is important, is because when reality comes, it would be necessary for Microsoft to play in this. So with that, I'll kick off with Q&A. Any questions that you guys may have?
All right, thank you, man. Why don't Emmanuel, you and I come here, and we'll kind of all make some of the items. So we'll open it to the audience. We'd love to get your questions here on the autonomy piece. Lex will help us with the microphone. And just a kind of quick thing, I wanted to ask you about one of the things I heard. You had a lot of systems that were like everybody's doing their own thing. Is Microsoft's plan to be the operating system of, say, automobiles and sell it to GM and Toyota and others so they can compete against Tesla and their data collection on automation and how they're doing it? Or is it going to take off in aerospace? Maybe that's why you're focused on that area, because you have someone like the Air Transportation Association that's like managing it from a level, and the same one in Europe, whatever the similar agency is there. There's no like rules of the road here. Is Microsoft planning on being that ubiquitous OS, and then you want to go into all these different companies that will buy your system and run your system like an OS, like a Windows on top of multiple platforms of a laptop?
So I think it's funny that we always get the OS question, if you will. In this particular case, I think if you talk about commercial, which is an area which I focus also on, sort of how do we create a business model, how do we commercialize our, I think the biggest focus here commercially is consumption of cloud workloads, right? So I think right now the AI race, especially in the industrial and enterprise category, really is that if these workloads are going to run on colos or they're going to run on cloud ABC. So I think one of these sort of commercial aspect is that if companies if this is the way to build next gen aircraft, or this is the way to build next gen car companies or cars, then a lot of these engineering workloads would need to move to cloud if they're not already on cloud, right? So we would want to sort of, let's just say, aerospace companies to do their autonomy simulation and training on Azure using AirSim. So it's less of an OS, more of an infrastructure play.
So in that case, is Bell Aerospace a partner with you, a collaborator? Are you a vendor to them to help them figure it out?
Yeah, I think absolutely. It's the vendor relationship. It's really providing the aerospace, as I mentioned, right? The other tools that we've built historically, let's take Visual Studio, for example, as a tool for software developers, right? It wasn't as ubiquitous this is my personal opinion. It wasn't as ubiquitous when it was a paid version versus when we made it free. When I was at Amazon, everyone uses Visual Studio Code, the free version of it. So you can conclude that, or deduce that entire Amazon is built on Visual Studio. So it won't be a far stretch, I think, to say. So it's about, so we're tool makers. So I think it's more about building tools for the aerial autonomy space.
Okay, we have our first question. So what we're going to ask our students to do is stand up and turn around to face the camera so you can see them. But we'll take our first question from the audience here.
Hello, lovely presentation, nice overview of the autonomous vehicle space. So the question I had is, a lot of countries are tackling congestion, as you mentioned, you were facing it by increasing adoption of public transport. And one would imagine having like autonomous air travel, air cars would just move the congestion up into the air rather than down. So what is the state of the industry in terms of autonomous public transport, like autonomous trains or ships or even planes? And what are some commercial things that can be done in that space?
I think did you say ships?
Yeah, I said ships because even logistics, I would imagine, be a huge business, and a lot of very trained naval captains man ships today. So I feel like that could be a possible space too.
Yeah, no, absolutely. So I think the bets are across the board, right? The car companies or automotive industry has taken. So there's no clear answer I'm going to give you, but I'll give you a bunch of data points that'll sort of kind of be summarized to sort of maybe try to get an answer that you asked the question for. So one is that so car companies, for example, they're building, they're rattled by, automotive companies are rattled by three things, right? They're rattled by EVs, Tesla did that, so everybody's on to EV. They're rattled by autonomy, so everyone's investing. There's every car company has a small R&D team doing some sort of autonomy. No one is building their own tools. They are using third-party tools. And then the third is that they're rattled by flying cars, right? Similarly, if you look at other modes of transportation, aerospace, or in the case of sort of ocean engineering, there are startups building autonomous boats. But the biggest chunk, in my opinion, the biggest sort of area of growth, if I were to pick one area where the growth can come and really, that can change the world, it is the sort of eVTOL space. Why? Car companies, and so eVTOL space is where you have a ton of startups. Most of them will probably go out of business. Some of them have started to, and the companies that are best positioned to build flying cars are car companies, not aerospace companies. Why? Because car companies have, in my opinion, have learned to be software companies a lot more faster than aerospace companies. Product life cycles are very long in aerospace. And aerospace companies also face a challenge that they have zero competitive advantage when it comes to electric propulsion, right? So it's the first time, according to some executives that I speak with who have expertise of both aerospace and automotive, they say that it's once in after 100 years nearly, there's an opportunity to break out the monopoly of Airbus and Boeing in aerospace and build the next generation aircraft company, and most likely it's going to be a car company that conquers that space. And why autonomy in the airspace? I don't know if I'm getting too off track. And I'm definitely sure I'm not answering your question, but I'll ramble through it again. And I think if car companies are well positioned to be a successful eVTOL manufacturer, and from a regulation standpoint, FAA, CAA, and the likes, EASA in NASA, EASA, in Europe and EU, I think they're a lot more serious about bringing regulation for aerial autonomy than any other modes of transportation. So having said all that, my answer is still, if I were to sort of pick one tech where there's an opportunity in the next 5 to 10 years, it is the flying car space.
Thank you. That answers my question.
I have one question, and then we have one question here. If you can pass this onwards. Thank you so much for coming here, or like being here and talking to us. You unfortunately missed an excellent presentation from the student. It was actually pretty stunning. Well done. And he showed a timeline of vision car, driving cars, and so on and so forth. What's your view on autonomous vehicles? It has been, I remember Eric Schmidt from Google coming up and saying, I don't think my kids will ever get a license. I think his kids by now become parents and definitely have a license. So the industry has notoriously been overestimating. I wouldn't say under-delivered, but what is the issue? Why can I not live on the beach and get into a shower every morning while drive the interstate through the mountain? What is stopping us from getting self-driving vehicles adopted widely?
Absolutely. So I'll tell you the problems. If I had a solution, I'd be sitting on a $10 billion company. But yeah, I'll share the challenges there, or one or two sort of main challenges. Before I answer, I want to bring your attention to, let's go back 100 years and see where have we made drastic, engineering design flaws, right? So take two inventions, TV and phone, right? So when phone was invented, go back, more than 100 years or, whatever. So it was wired, right? For a better part of the last 100 years, phones were wired until I think, late 80s, early 90s. I was born in 80s. So I've seen the wired phones, and I've seen wired phones and internet over those. And then from there on, rest is history, right? So phones were wired, and now phones are mobile. They should have been mobile. TV was fixed with antennas. And then TV became, so TV was mobile when it was invented at invention time. With the TV sitting in one place, it doesn't have to move, but yet the antenna is mobile. The delivery of content coming into TV was really mobile. And phone was the other way around. We fixed that engineering flaw. It took us 100 years. And now it's like, mobile phone, iPhone has really changed everything, TV everywhere, everywhere, everything is on mobile. So having said that, I think there's a major engineering flaw we've got, or design flaw we've got, which is the roads we've got are meant to be driven by humans and not robots. So the problem, we don't have infrastructure for self-driving cars. What does that mean? We probably need to create new cities that can accommodate self-driving cars. That would be one sort of thinking, and a lot of people think about that. And that's why I think that's one of these sort of reasons also folks building flying cars or aerospace companies, focus on R&D for autonomy. That's what they say. If you talk to military folks, we have a PM on our team that focuses on our defense business, and defense doesn't have a lot of problem. It's much easier. This autonomy problem is much easier to solve in defense scenarios because they're not worried about They just need to take payload from point A to point B, right? It's regardless, they don't care about a flying car or a robot coming back to the from where it flew. It was really just getting from point A to point B, and so military applications are very different, and they're seeing a lot of success, a lot of funding. DARPA is sort of underwriting it. I'll come to DARPA point. That's my last point with respect to this question. The second is another problem, which is, the state of AI. One of the things that we look at is, and I look at, in my day job, is the creating business models for AI. Right? Do we really have a business model for AI? It's a hard challenge, right? There's a lot of Chat GPT or partnership with OpenAI and so on and so forth. Who's going to monetize that? I can't say. So let me, offer a little bit more, some data points. The first era of business of software that Microsoft pioneered, for example, was the era of, and JB, you would know this, and all the professors in computer science departments and business schools know this, and have sort of written about this a lot, is the zero marginal cost. Before software, there wasn't a business in the history of mankind where marginal costs were zero. With software, marginal cost of a commercial software was zero. And that's why, the Windows 95, the Office, and that was the sort of era, because you could create software once and sell it to 1 million people or 10 million people. The marginal cost of that sale was zero. So the profits were amazing. Then, came SaaS and, cloud. The marginal cost, and I know a thing or two about cloud business, having run one of the top 50 businesses at AWS. The marginal cost of cloud business or SaaS business is not zero. There is marginal cost, but you do see the economies of scale as you grow, enormously. And economies of massive scale. There's no research, I just invented that word, but economies of massive scale is what you see in cloud business. And that's the sort of gravity why enterprises are shutting down their data centers. In Princeton here, there's a company, I think it's public info, S&P Global had a big data center in East Windsor in the Princeton area. They shut it down. They completely wiped that off. All of those workloads moved to AWS. So although you can argue that large company was operating at scale, yet not reaping those economies of scale that they would want to. So economies of massive scale is, in my view, an economic rent that we did see and we do see in large cloud businesses. In AI, it's different. There are no economies of scale. Currently with these large models, you see diseconomies of scale as you grow your large AI business model. So that's I'm not a genius and I can't conclude this, but that's what my finding is today. That it is AI businesses are hard. So look at public companies that have gone public. I think C3 AI. There's a defense company. Those stocks are tanking and they aren't able to turn a profit because they can't show neither the software, business, the software 1.0 business level scale, zero marginal cost, or the cloud or SaaS business scale. And AI businesses are generally very hard to monetize on. So that's another point. Last point. So let's talk about how we train, why simulation is important, and how we train autonomous cars, autonomous planes, flying cars, and all the autonomous agents today in simulation, why simulation is important. So as far as autonomy training is concerned, simulation is important for one thing and one thing alone. You need to generate a lot of data and the synthetic data. So you need some fake data. So a lot of the simulation generates a lot of fake data. You can use that fake data, which is near realistic, to train your data-hungry deep learning model. Now, how does that apply to not flying car, but a regular car? So a teenager, I have a son, he's 14, in 2 years, 3 years, he'll start driving. For a teenager, on average takes about 18 hours of training to intuitively learn how to drive a car. Now, so there's a lot of knowledge. So right now we've gone from supervised learning to unsupervised learning to deep learning. and so on and so forth. But we don't have a killer machine learning model that will solve this, or paradigm. There isn't one. So let's talk about deep learning and how that is very challenging today. So a teenager takes 17, 18 hours to learn how to drive a car. So once my son knows this, right, he would know that driving a car off the cliff is a very bad idea, because we as kids have learned it through riding the car with our parents when they were driving. So there's a lot of intuitive knowledge, and with the very little training, a human is able to get up to speed on how to drive a car and know that driving off the cliff is a bad idea, right? Unless a human is absolutely crazy, would not drive a car off the cliff. Now let's talk about robots or self-driving car. Now, for a self-driving car to know that driving off the cliff is a bad idea, the car needs to fall from the cliff a few thousand times, 10, 20, 30,000 times. So car has to fall to learn that, hey, falling off the cliff is a bad idea. And then the car has to fall off the cliff after it has learned that falling off the cliff is a bad idea. Now, car has to fall at every possible intersection, every possible scenario where it could actually fall off the cliff, thousands of times to avoid falling off the cliff in any given situation. So that means the training that is required for a robot to first learn that not to do this, and then to make sure that it doesn't do it in every given scenario possible, you require simulation. And that's why AirSim and all these simulation pieces exist. So that's, I think, the major challenge. Jan LeCun, last point, and quickly I'll finish. Jan LeCun has mentioned that self-supervised learning may change that, and that's why we don't have self-driving cars. One area of researchers, product developers, engineers believe that we do need yet another breakthrough in machine learning algorithms and underlying paradigms to get this problem solved.
All right, let's go to our audience for our next question, and we'll have the students stand up and maybe come a little closer because the camera's more this side and give you your question.
All right, perfect. Okay. Oh, hi there. My name is Yoshan. So I represent the EMBA program at Cornell, Johnson. So because I don't drive, right, and I have a profound appreciation for self-autonomous driving vehicles. And I think when I was doing my undergrad in 2010, I was hopping on the hopes of seeing self-driving vehicles come out sooner. But it's heartening to see the training of unmanned or semi-manned vehicles, particularly aerial vehicles. In this case, with AirSim, I think it's good development to see that, and good development to see as well when it comes to experimentation. However, because I'm risk averse as well, I see the close association as well between autonomous driving vehicles and cybersecurity as well. When it comes to the business of cybersecurity, in this case, there could also be, we also see the likes of, malicious agents doing packet sniffing as well, and then potentially affecting, the pre-trained models that we have today. Are there investments made, alongside AirSim, with this realm of cybersecurity, with this particular use case of aerial vehicles?
Let me try to summarize your question and tell me if I got it right. So you're trying to say, hey, we have a lot of challenges with cybersecurity. There are privacy issues with large language models, and a lot of these autonomous systems also use pre-trained AI models, which is essentially one of the things that we do also. So what are these cybersecurity implications? Is that fair?
Yeah, potentially. So two things. First, the data is collected as well. From the on the local level from the vehicle itself, and secondly, malicious agents potentially tampering with your pre-trained models as well, causing any kind of accidents. So that's the kind of risk that I'm envisioning as well in the future after we have sorted out the autonomous driving piece. Yeah.
Look, I think that's probably the hardest question that you asked me. I'll tell you what I know. Short answer is that I'm actually not qualified to even answer that question, but I'll tell you different pieces and briefly. So first, and what you asked is a very complex question, and it requires a very comprehensive sort of answer. And I'm probably not the best guy to do it, but let me address a few things. So one is cybersecurity, like hacking of autonomous car, or autonomous plane, etc. So I think, again, layman view, again, I can, we can take this offline. Maybe, maybe I can refer you to some aerospace engineer at an aerospace customer company who's looking at this. I don't come across this day to day, but I would assume that cybersecurity of traditional connected car and autonomous car is probably the same, because an autonomous car or autonomous plane is not more connected or less connected than a traditional one, right? So with a lot of a lot of the compute, eyes and ears and all the sensors of the robot are on board, right? So I think it's if the robot is like disconnected from the internet, right? The only way to sort of hack into is through internet. So I would say it's probably, my hunch is that it's probably similar to what a traditional car would be, because there have been cases of going back 4 or 5 years where a Wired magazine, I think a bunch of articles where hackers were able to shut down cars, traditional cars. People are sitting there and they could shut down the cars. So I would say implications would be same. I'm not the right person to answer that. The second question you asked about the language models, right? So in Microsoft, there is a research group focused on privacy preserving machine learning. I think those challenges could be solved by employing the privacy preserving machine learning algorithms, making sure that your language models are not leaking information. And there are many technologies being built, both at the algorithm level and the hardware level. At the hardware level, it's confidential compute, which is basically providing security of your code at runtime. So there's a lot of tech being developed, but they're all different areas. They're focused on sort of privacy and really hardware compute with confidential compute. Yeah, I think that's what I would say. I think there are 3 other areas. Very close. I'm very interested in these areas. I look at it. I read a lot about this. I talk to a lot of PMs or engineers in these areas, but personally, I'm not involved. I can't say more.
All right. Any other questions from our audience? One thing I did, but Nikita? All right. We have one more question from our audience. We'll have it stand over here.
Hi, my name is Nikita. I have a question. Hi, can you hear me now? My name is Nikita, and I have a question with the automated cars with self-driving. Well, not necessarily self-driving, but just driving cars. How realistic would that be? Not even just in technology, but just logistics. If you have cars flying around and they can fly into buildings, or if there's like accidents that happen in the air, just the risks to people on the ground. So how do you mitigate the risk so then that could be something that's practical? Thanks.
Yeah, so yeah, I think this is there have been a couple of cases in Ireland and in Australia and in the US where drones, the delivery drones, flew into wrong places, and they brought the electricity of a whole city down. I think those are challenges. I think regulators, FAA, EASA, CAA in the UK, those guys are looking at it very hard, and there's a certification process. Yeah, so the industry is looking at UTM, the uncrewed, traffic management systems. NASA is doing some groundbreaking research. We're participating with NASA in putting together something of a reference architecture. And NASA has done a lot of work, actually. It's all publicly available. You should search on this, the UTM software. So yeah, it's not something one company will solve. It is something, a job that a regulator or a consortium of regulators like EASA, NASA, FAA, CAA, and they're thinking really hard.
We keep hearing lots of cities of Dallas, Los Angeles, and Melbourne. There's something those 3 cities are doing a lot with what at the time was Uber Air, whatever they wanted to call it. What's happening there? Are you clued in with that? Can you share any insights on why these 3 cities? And the key word was LA's going to have it before the 2028 Olympics, and you could actually fly from venue to venue.
So Seriously, I have no. I do know. Dallas is a lot of aerospace companies are in Dallas. I can say I don't know. I don't have any insider info, but I can tell you that a lot of our, so for example, some of our customers are based in Dallas. Google's Waymo got the sort of permit to. I think it's more to do with regulations. I would say. I don't know if there's any political relationships behind all this. I have no idea.
Let me ask you this: what's the holdup for this? If you've got Tesla and all these cars on the road, and they're tracking every mile, every kilometer, they're building their data set. Waymo's doing the same. Does the industry need to come together to bring all this data together? What's holding it back? Like, we've been waiting for this for so long. What's it going to take, and especially for this group of next generation business leaders who are going to be coming of age when their opportunities will be facing them on this new frontier? What's the holdup on this industry to keeping us from there?
I think just to summarize, it's a summary of all the questions and all what you asked as JB is the summary of everything we discussed so far, right? One is every car company is inventing their own wheel. The wheel was invented once and was used everywhere. But right now, if you look at the simulation and synthesis tech stack of each company, it's different, right? Tesla, if you look at Tesla, my personal opinion is probably the world's #1 applied AI company, right? There's no company, Apple is also another one, right? Applied AI, where they necessarily don't invent, like we invent a lot of stuff. These companies, at least Tesla, they're able to, apply technology in a way that nobody else does, right? So yeah, either a winner takes all, kind of rent, a winner emerges who does that, or industry consortium that says, hey, we don't need these separate tools. Let's not have this Game of Thrones, and rather just, build open source tech or a tech that can be used by everybody else. And lastly, I think it's that training problem and the underlying paradigm that I talked about, that we need yet another breakthrough in AI, in machine learning models. The current ones, the deep reinforcement learning, is not going to cut it.
Okay, well, this is an emerging technologies class, so everything's right on the edge. Anybody else want to ask anything before we close it out? One last thing I wanted to ask you. You work in the Chelsea location for Microsoft's R&D office in Chelsea, not the Times Square sales office, correct?
Correct.
We have a lot of very interested folks, and like big tech companies here. Can you give us a little bit of insight on what is Microsoft doing in the Chelsea office in R&D, other than what you're doing, but give us a little insight of what it's like to be an insider there.
Yeah, so if you're planning to do a PhD in computer science or other areas that are of interest to MSR, there are a lot of internships still open for MSR. It's JB mainly researchers at MSR that work out of there.
Thanks, Fahad, for sharing your time with us. Thank you so much. And if you were here, we had a little token of our appreciation for you. We'll try to send it out. Thank you so much.
Yes, we appreciate it. Thank you.
Yeah, thank you so much, and JB, thanks so much for the invitation. As a penalty for not being in person and still get the credit of being there. If any one of you is in New York City, you are in New York City, but if you want to reach out to me, and I'm happy to connect. I'm /Fahad on LinkedIn and Fahad Khan on Twitter. So please feel free to reach out, and Fahad Khan at Microsoft.com also. No dots, no spaces in between. So Fahad,
I'm sure some people in this room will take advantage of that. Thank you so much for that. We have a strong relationship between Cornell and Microsoft. We want to keep that going strong. So thank you so much for that offer.
Thank you.
Cheers. We've been going for a little bit. Are you guys okay to go a little longer, or do you need a little break? We just wanted to close out some things on the course. And this will be, we realize we finished already. This is the last minute. Do you want to take a little break? Are you okay? Or can we talk for a little bit?
We can, before anybody is getting too uncomfortable, you guys can go and fill out to the blue anytime. Right? So do it easy. Yes, that was the first time we did this course. As you probably realized, we had this course idea how long ago?
We've been pitching this for a while. Yes. And again, I think I mentioned the first night, it got approved December 3rd.
Yeah.
So we pulled it together really fast.
Like it got approved December 3rd, and then it was like it never appeared on the schedule, and we kind of like, will we ever have students? Then we got students, but they happened to be on a trip to, where was it, China?
Tel Aviv.
Tel Aviv.
And then I had to add you manually because the system still doesn't have you. We will get your grades in before the end of the term somehow. We'll figure it out.
So, but that was the course. So, I think we want to do two things. First, I think it is actually three things. It is a good thing for us to reflect through all the topics because they're not randomly chosen. They were actually chosen with like over a lot of things.
Like 15 or 20, didn't we? We narrowed it down to these 10?
Yeah, we discussed quite a lot about which topics to choose, and we want to bring the org together. Why those topics? What we hopefully could show you. And then the second thing is, we would like to get your feedback, obviously. Should we do this again? Did it work for you? What's the thing, right? And then the third part is, since we're up here, quiz us, ask us anything you want, and we will come up with an answer, whether you like it or not. How about those things?
Any questions from the course? The speakers, by the way, some of you asked for the speaker presentations. Almost all of them had said yes. I'll get that up there in the next 48 hours. I'm flying home tomorrow, so I got 6 hours on the plane to get it uploaded, so I'll do that. All the videos are out there. All the information we got ahead of time, all the photos. There's a ton of photos out there for you if you want to recap the course. I'd love to hear your feedback on the topics we did. What you'd like to see next. What do you think it should be there? We'll probably put ChatGPT in or something. That's
Let's do first a quick recap. So for us, the important part was to expose you to areas which we can't cover so easily in our class. Because when an industry is hip or hype, right, then the margins are good. That means they pay you better on average, right? It's a very logical conclusion. One of my mistakes I did, well, it wasn't a mistake, but as I got off my MBA and Dell Computers hired me. The Dell Computers at that time has been around for 20 years. It was awesome for me. I became a very good management education. I started off after my MBA with a team of 60 people, which I left. It was good. And Dell did a lot of investment in me so that I become from an clueless MBA to a manager. That was good. But, the payment to be in a retail industry where every margin is turned, obviously they do this on every employee. I won't say the Dell is doing this, obviously not, but figure out where you want to go. And growth industries is a good place. Now the second thing, so that's the reason why we brought them in. Now if you look at all those industries, what they had in common is it is always about how do you apply the technology, how do you make it feasible. Unfortunately, I tried to, at our last class, why isn't it deployed? He kind of talks about because the roads are not made for those cars or so on. So, you can turn it actually around. We haven't managed yet to make it actually part of our normal workflow. And then he says, well, the data is not sufficient to make it part of our normal workflow, right? But it's always about how do you bring something like robotics, like self-driving vehicles, like quantum computing into our normal work life. If there is not a market, but it sounds sexy, don't go there.
Always follow the money. The economics always win. And you heard that all this week. There are holes in almost every one of these. And then we were kind of hammering on that. You guys asked some great questions of our speakers. Not everything's going to take off. And you got to know when to go in. It is high reward. It's also high risk. The concept we want to get across here, and I mentioned this a little bit in the first class, is to use these 10, look at these, and then have a framework upon which you analyze these new tech. When I talk to senior executives, a lot of times they'll bring people like us in and they'll ask, what about this? What about that? They'll read the article on the airplane or something, and they don't want to miss. You're also going to be in that role very soon. You have to kind of place the bets for your company's resources, and that's people and money, time, and do you throw a little over there? Because we don't want to miss out, but it may not be the right time. It's a lot about timing and bringing these together, and some of these things will need each other. maybe we won't ever figure out the autonomy space till quantum gets set and we can do massive computing. Like there might be pieces that come together. And as we get more convergence in the tech space, you see that. But unless you're exposed to all these different things. By the way, did you guys hear things this week you did not know, you're unaware of? We've opened your mind on a couple things, hopefully.
And then we did our job. Yeah. No, but the second theme, which I thought went through nicely, and like this is the reason why we chose it, nicely through the whole class, was that there is always a business battle to be won in every new technology, right? So you saw, and I know I repeat myself, but I think that's the thing teachers do. Essentially, we showed you many industries where it is not clear yet whether it will be a platform play, whether it will be integration software, hardware play, or whether the software or the hardware will win, right? And it was always, you have a space, you have a new technology, there is a clear sign of it might be amazing. There are, like as we saw in self-driving cars, actually maybe not yet, right? But there's a clear hype around it, there's a sign. The question is, are you going to the software group or are you going to the hardware group? Are you going to the integrated group, right? And I think if I would reflect, and I would be now in your position and kind of, for robotics, I would not go to a pure software play after what I've heard, right? Because he essentially says it will work, that it's separate, that there is a separation between software and hardware will come when regulation kicks in. So if I go to the software player, despite being in a very hip place, I might fail out because I don't get the hardware to work.
And David mentioned the software play on quantum computing,
yes, right?
Which I did not expect to hear.
If I go into the AR world, I probably go to a software player and not to a hardware player, as you heard yesterday from Christoph. So figure out the space you like, but as well, towards the risk mitigation, find what business, and you like this will train you on. Think about the strategic setup, which makes it more successful or not. Helping you to understand what is the lever. Is there a market? Follow the money, but is there a lever on the right side? Because when the industry is growing and the company is growing, I lived in Google, right? You had those folks which came in year one from Google. They are like amazing VPs and whatnot because they were at the right moment at the right time. They just float up. And when times get tough, like they just do, then there's like, oh my God, we don't know what to do. So, but you want to be on that surfboard. Life is beautiful when you're on that board, right?
And this is the time to take that risk if you do. I talked to a lot of students the last, I'm thinking that, what about that? They almost get into analysis paralysis. So you might make a mistake. It's okay at this point in your career. You'll go into some new technology. It might not have taken off, but it will open new doors and windows because you've learned so much from it. So as venture capitalists, we're always looking for an entrepreneur that's failed 2 or 3 times. They're actually the best ones. They turn out to be the most successful. So obviously we want you to make the best decision right off the bat, but don't get so afraid. Now I also know some of you are here, you're looking for a strong company for a visa partnership. You only have 1 or 2 years in the country, 3 years after graduation. It's your ticket to stay in the United States. I totally get that. Those are those Apples, Microsofts, Amazons, Googles of the world, have whole departments that can help manage that sponsorship process. I get it. I totally get that. But if you can, go for the most opportunistic thing. Even if it fails, there's so much learning that occurs from that, you'll be fine, especially with the Cornell degree behind you. We have a tremendous alumni group, and even like our Cisco team that we met. You may have failed at this thing. They knew it was a technology that didn't work, but that's a knowledge base. It's like an extenuation of the MBA and the graduate degree that you will just bring with you to the big company. So
I actually think you are, I love this pitch, but my ambition with Cornell is even lower here, because the folks who have talked to me know this. For me it is, think twice before you go into consulting. Think twice before you go into investment banking. because you come into an organized, structured setup where you start and you go through the ranks. There's no shortcut. There was shortcuts. There was growth. Now you are in your wheel.
And you realize it 3 years in.
Yes,
You're like,
and you're going through it. So make very sure that which industry, I just said I went to Dell Computer, so I obviously was a dummy and didn't follow like the hype circle, but make sure that you actually understand that there is potential in this, is potential in the new industry. If you go to the very clear path route, then that's what you get, a very clear path route. Maybe that's what you want. But on that clear path route, no shortcut. Not the growth you might get at a Google 30 years ago, 20 years ago.
And the best thing you can do is stay curious. You only have a year here. Go to all the events, all the guest speakers, understand, get exposed. Hopefully we've exposed you this week. And you'll make better decisions, I promise you.
There's a third thing. So we had the industry part, we had the business part. There's a third thing which I actually think is a kind of a magic trick here. No matter which industry you're actually looking for at the moment, and all of industries have this, integration is a key part. Integration / user workflow, right? And we always ask, like, okay, what's the user thinking? How does this make, like this, all those two areas? Now, I'm very cognizant of the fact what type of profiles we have in this class. So, user thinking, that's spot on PM work. Like, get your UXR partner, think about the user, think user first. Voila, you learned this here. You can apply this no matter which industry of the 10 which we showed you, 8 which we showed you, you're applying to.
We just only had 8 speakers.
Okay, well, yeah, okay, well, you showed 10, we showed it. No, and the other one is integration. When you are more of a technical background, that's it, right? I mean, think about it. Very often, APIs, platforms, bringing things together, that's the hard part. So if you can kind of say, look, this is all nice. I learned about this cool now you have industry. I can now spell quantum. Why should I actually be allowed at Microsoft? Well, IBM. Well, because they have a need for, is it integration? How do you think about platform integrations? How do you think about computer and industry design? And they have a need for user design. Those are the 2 core things you have learned at school always and always again. But we are now only saying we take hip industries and we don't. I mean, we're obviously walking on water and rocket scientists. No, we are finding those same principles that you learn at school over and over again.
We're the industry guys. We're the adjuncts. We come from industry. This is a part-time job for us. Hopefully we can combine that with these amazing research professors we have. By the way, we're doing the talking. Conversation for you. Thoughts? Things you want to share? Go ahead, Brian.
Interesting. First of all, I just want to say appreciation to the 2 of you. I think it's from all these 4 days, I think, it's true. We are very exposed to all these things. I personally think that we should have done this like before we even start the program, because that makes us sort of like well aware of all these other kind of like points. And I also know that I'm very sure that it's very difficult to gather all these like speakers. So I really appreciate the 2 of you. Because I think they're very like high quality. I think.
By the way, we shot high to try to get the best speakers here, and those are the hardest ones to get on their calendar. Yeah.
So all my previous class, I think this has the best group of like speakers.
Oh, thank you.
And my personal question is more like, you said that you think about like 15 industries that you're like weighing. I'm just curious about what other industries were you like?
I wanted to do space and space travel, space mining. I think there's a huge industry that's going to open up in space. Maybe travel tourism stuff. It's probably too early for that though.
I wanna, so there is nanorobots you put into your bloodstream to actually find healthcare and like fix your body from internally. That's actually pretty stunning. They are on the first human trials. Speakers, unfortunately, we have at this moment we have the
the JP Morgan healthcare conference in San Francisco. I was like, no way, this is all my money.
We always also looked at East Coast things too.
They were like, he would have come over. Then we had he would have gone. But he couldn't do it. And then we looked at, there is a hole on the NFT platform distribution part. We looked at this. We looked at different cybersecurity areas, which is a good one. But then you have to choose for cybersecurity, for example. On those 3 points, I can't really make the separation point on the business case. It's a software, and we wanted you to understand that everything you have learned at school is easily applicable for all those industries. Don't get blown by the hype thing. Make sure you understand what hype thing is out there, but don't get blown by. Because sometimes, self-driving cars hasn't worked. So you have this.
Other thoughts, comments? Anything you want to share?
Questions?
Issues? Complaints?
Yes.
Another recurring theme across all the lectures is optimization that kept coming up. And also I wanted to mention the sort of perseverance you both showed in the face of the team having to reschedule things around speakers who weren't communicating, just sort of went through it, and that taught us as well, from my point of view. And also as a CS student, I wanted to ask if there were any MBA courses you might recommend. You may not know now, but any MBA courses you might recommend for us.
We can maybe take
that. Is actually a very good question. So you the course we are teaching, we always have a combination between CS and MBAs because we are in a collaborative world, right? It takes a village for many, many things in our life. So that's the reason why I actually love it when CS or design students turn up at MBA classes. So absolutely cool. That's the reason why I'm glad that we got again today a good selection of the best of the executive MBAs here. My suggestion is take up the offer, like they are, like you ask some of the MBA students, they know which courses are good. Come.
Yeah, my biggest thing when the engineers take my courses, they're not familiar with case analysis. And MBAs, we live on it. And they think about problems differently. I'm an engineer by degree as well. And I see a little bit of the differences amongst us. My biggest thing to encourage all of you, but especially those that come from deep technical backgrounds, is just up the professionalism game. You wore a jacket tonight for our speaker, and you just looked professional, and it was nice, and you came 2 hours early to help him. Looking at the monitor, there's a vanity monitor right there. Like, just upping your game of what I call executive presence. You'd be amazed how much you can overcome some of your deficiencies. Just even if it looks good, even if it sounds good, if it's not as good. I would encourage that. And coming from that nerdy, geeky engineering background, that's the best thing I could have done. And this campus is ripe for that because we're combining business and tech together. Absolutely take advantage of it.
I can tell you I'm doing the design data products course with MBAs and CS, and some of you have done it. And I always have to chuckle because when the groups, so there was a time where I selected the groups and put people in as diverse, and it always created, I don't want to talk to them. That's why I was like, honestly, guys, whatever. It's less time for me. Like, let's work for me. You go and you select the groups. So some of the groups will CS people under themselves, and some will be MBAs under themselves, and there is a natural selection process. It's very funny. When we have split groups, what I get to hear is, gee, these MBAs, they come together, they talk, and nobody's working, nobody's shipping code, nobody is doing stuff. It's like, well, yeah, okay. And then, but if I see only CS folks, there's like, we don't actually know what to do. So they say we can build something, but they actually don't know. So it's actually very funny when, like, the groups in general, that's a very rough oversimplification, but it's true on the edges. Pure MBA groups,
normally come back with an Excel model and some slides and a good vision. Pure CS groups come back not only with one model. They normally use Vector, have 6 different iterations on the AI model, have done a nice integration from few data sources, but just went to Kaggle and downloaded everything there because I didn't know what kind of business model they wanted to. So it is a combination of you both, which makes
is work with each other, like force yourself to go outside your comfort zone there. As a venture capitalist, there's kind of a formula we look at. It's usually an American and a foreigner. It's a tech person and a business person. And it helps if it's a man, woman, white, black, that combo. And if you look back, like, you know, the Google founders and the Apple founders and the Microsoft founders, and that combination, just the skill set that comes together. As a venture capitalist, I will bet more on that because the odds are they'll be able to handle more things with that diversity. So if you're a business person, hang out with the tech person, hang out with the business, and you'll cross-pollinate and learn. That's what this whole campus is trying to get across.
Any questions? Other questions? You can ask us.
We're keeping you, so you know.
Go for it.
Hi. Well, first of all, thank you very much. So, next year, if you have this class again, I'm sure the top 10 will be maybe the same or different.
I hope it's different.
But how do you keep yourself exposed to a variety of emerging technologies and markets? In 6 months, some of us will go into a certain industry, for example, consulting or tech, financial services. But when you actually go in there, you're sort of kind of stuck and you're kind of narrow-minded. But how do you keep yourself open and exposed to learn different industries?
So I can tell you how I got to Christoph, the speaker you had yesterday. It was deep research. I went to a Christmas party and had a couple of mulled wine drinks. And then this dude next to me called Christoph showed up and we talked. And I realized he told me a little bit about what he's doing. And I was like, wow, this is cool. And I started chatting and we talked and I asked more questions. And after a while, I said, actually, I have them with me. I was like, oh, cool. Can I see them? And he's like, yeah, well, I guess so. So he went into the room, got his bag, and then he did what you guys showed and was like, well, this is so cool. Do you want to come and talk at the course, right? I mean, why do I tell you this? This is a very profound. Not every speaker was that need to get. I mean, he was complicated because he lives in the West Coast, so it wasn't easy for me to arrange this, that he's really here. But finding him took only one thing: curiosity. Curiosity and stay eager. You have heard this. This is such a lame sentence, but it's
stay hungry, inquisitive. Yeah, and I couldn't agree with that more. You're just always if you talk to a salesperson, they fly a lot. They'll always talk to the person next to them. It could be the next CEO because usually people that are flying, they're business people, especially in business or first class. It's that natural ability to just go and just be inquisitive, just start opening. For me personally, I listened to a series of things. I'm going to use ChatGPT as an example because you know how it took off. About a year ago, I started hearing about this. What is going on? I knew OpenAPI, but I didn't know much about it. I am a big Alexa fan. I have 6 of them throughout my home. I have a feed of snippets so I'm brushing my teeth in the morning. I tell it to listen. So while I'm brushing, I hear the feed. And I have Wall Street Tech Journal and a whole bunch of others. And you start hearing there are 5 things on ChatGPT. Then I go and investigate it, and I figure out what's going on, and then you go into a rabbit hole diving in. But then you're like, whoa, this is serious. You understand the power of it. And, there'll be something new. This time last year, no one heard about ChatGPT. Few of you knew about OpenAPI, but not many, the company. It's that inquisitiveness. It's in you. I mean, I know you have it because you're here.
You're 40 and you say, I want to learn about quantum. You have the speaker. That makes cool people.
Yeah, Jason, are you considered an expert now in quantum? You feel like you know everything from the research?
No.
But you did do a dive in it, right?
Yeah, I mean, I actually did some of it before as well. So I did some coding on Quizlet just to try it out because, but it's so complicated. Knowing all the vector math to make the qubits work, and trying to understand, I did engineering for my undergrad, but I haven't done linear algebra 5 years.
Right,
You
and
already learned that it's like a huge pain in the butt. So I think
There is a YouTube channel that I subscribe to, and the guy, it's not just some guy's YouTube. He explains mathematical concepts with graphics.
Oh,
I'll have
yeah.
to send it to you. You know what I'm
Yes,
talking about?
nice, yeah.
With the glue.
Glue one brown.
Yes, I'm like, I remember that from like my junior high school year, but now I get it. Yeah, for some of us, we need that.
Michael.
Yeah, so I just want to extrapolate on the whole curiosity thing, especially for us in our careers. We're told that at one point we have to specialize, and we see all these different topics; they're all exciting, and we don't necessarily want to make like that investment and choose the wrong thing. So, what's your advice on that? Like making that process?
So there are typical types, and I feel very comfortable to talk about one type because the reason why you're here, you're self-selecting folks. If you would have known what to specialize in, you would have not done an MBA. You're clueless and you're scared. That's the reason why you're here, right? I mean, I have been an MBA. I can say this. I'm clueless and scared. That's the reason why I did my MBA. Like, if I would have known what to do in life, I would have done it instead of paying money to sit in a classroom. So MBAs are inquisitive. MBAs look for things. MBAs want to test out new things.
All graduate students, because not all are MBAs.
Yes, true. All graduate, but we turn around things and kind of look at stuff, right? That is part of our nature. As I did my MBA twice, and one time I did it for myself, and then I sent my wife. Like my wife went, and I followed her as a partner. So, at that time, we had this young au pair. And she knew exactly what she wanted to do. And she told us all her life, like how it's just planned out. And my wife and I mean, like way older with kids, we were looking at them and she left her upstairs and we looked at us like, wow, we wish we would knowing what to do tomorrow. So that is a type of person. Now there are other people. I worked for the CEO of Deutsche Bank. The CEO, right? Not like from like who owns everything, investment banking, retail banking, and so on. And he, after I left Snapchat, he called me in, and I flew every other week over to advise him on data and product stuff. He's my age, and I know him well, and we chat, and I really appreciate his skill set. But if I think about like what I've seen and all the different things I did, I think like I know more. Like he makes way more money, trust me. And we invest in companies together. So he came into San Francisco and we looked at companies and the way he would invest. I was like, okay, well, I can't do that. But so it was a little bit frustrating. However, I would not take his life because he entered the bank as he was 17 years old. And, like this is Frank Sommer. Like he's not the CEO from the retail at the time, but he went through the career always at Postbank, which got acquired by Deutsche Bank, and then it became Deutsche Bank, and he was like, this was his line. It wouldn't be a life for me. So if you tell, like he would say, yes, specialization has helped me. True. And it's his type. Folks in this room are most likely not one of those specialization types. Now, if you feel that you like to specialize and that you are happy, then go for it. I bet you don't, because otherwise you wouldn't be here. So that's my 5 cents.
And that's because change is hard. And most people are afraid of change. You guys will not be afraid. You'll pivot when the time is right. You'll see that it's the wrong. I had 8 jobs and 9 jobs in 8 years at Microsoft. One I had for like 3 months. I'm like, this is where I'm going to go, 4 months. And as soon as I got in, I realized technology's dead. Got to get out. 2 years later, the division's dead. So all the work I did, got to pivot. And change is hard.
Take Pete, the guy from Google, the clinician. I mean, I have such a high respect for this guy. He is such a smart person. And he built his career as a chair of a hospital, as a doctor. So he went in, he is a pulmonary doctor, highly specialized. But he got more and more interested in technology. So he started doing stuff on the side, trying to
be interested in technology, trained himself. He came up with a system of checking with nurses because he realized that nurses more often have a gut feel which doctors don't, so he created a mini computer program to capture those nurses' feeling to actually start to rely on a signal. Like amazing, like he reinvented himself constantly. And then he came to Google. Then he was at Google, then the pandemic started hit, and he's like, actually, guys, I still have my calling, paused for Google and moved back into the hospital in order to work on COVID cases because that's the pulmonary doctor's calling. He actually had to say goodbye to his wife, this Rachel guy he talked about, or some of his students talked about, and said like, I don't know how dangerous it is. I take a little flat, we do WhatsApp calls, and I hope I see you again. And then he vanished off and he worked, he left Google again, worked in the hospital, constantly 24 hours, and then after a while, after everything came back, he went back to Google because that was his calling. This reinvention, this flexibility, this kind of saying, I'm doing the right thing at the right moment, which excites me. That makes Pete. That makes him pretty amazing.
Do you want to say something?
Just kind of like, for most of us, I would say, especially coming out of the MBA, when we look at companies, we're looking at the ones that provide us the most optionality, which is like a proxy for like what company gives you the most prestige, like the most money. And then people choose like their passion projects afterward. But it sounds like what you guys are saying is like, you want to maintain the optionality. And I'm just kind of curious to hear your thoughts on like, is there like an inopportune time to move to like a smaller company and take that risk, especially if it goes belly up?
I say when you see it. This is what I mean. It's not going to be your decision. You're going to see something. You're going to be like, wow, this is about to take off. This wasn't in my plan. I was planning on staying here for a year or two, but that is a window that you will take, and you'll just know it when you see it. I did it. Lots of people have done it. I regret not opening that window. Sometimes I've seen it. And I'm like, ooh, I'm scared. I got this house payment. I can't. I should have done it. And if you do that leap, because remember, the tech is changing for you guys even faster. It's hard for us. It's going to be really hard for you. It's just the pace has gone crazy. Go ahead and take it, and because the failure rate is high, but also the reinvention rate is higher too. There's more stuff coming out. So I say take the risk. You're smart people. You'll figure it out. I really believe that.
Life is too short, guys.
Well, that's coming from old guys.
No, but like, I mean, think about it.
They got student debt they got to pay off.
No. It's cool. That's the reason why we say go to industries where you get paid and take the risk because you have the knowledge to take that risk. But when I say life is too short, is do not look for industries, and I do not look for high pay. Look for high reward. You can. I just listened to this blogger, and he talks about that you can calculate everything in time spent. How long does it, like instead of cost, right? What's the cost for going to the cinema? It's 15 US or so, or 10 US, right? And or dollars. But if I look at it in time spent, it's 2 hours with my daughter. Hey, that's a completely different model, right? What's the cost for like doing yet another thing? It's 2 hours of my life. Think about time spent because you do have a very good notion of time spent. Let's take Warren Buffett. You all know Warren Buffett. He is super rich, okay? He's good health. He's in good health. He is fit, mental fit. He's fit. He's over 90. Oh, he's 90. 92. He's over 90. Does anybody wants to switch with him? Get his body, get his life, get his money? Nobody of you would take. You are happy to be way poorer than him because you have your whole time in front of you. So don't waste it by going somewhere where you believe, oh, they pay me. Because when is your party, right? So for me, it is, and I can say this because, like, you guys know my happiness with consulting companies. I had in my life, I had in my life 4 times possibility to go to one of the top 5 consultants. I always was tempted, but I always turned it down.
I did it, and I'm telling you, it's an MBA on steroids. You learn so much, but it kills you. But it's a great investment.
And it was. Like you see, like
See, it's time to cut off. Listen,
like,
are you guys ready to go? I'm hearing zippers. Let's give them a little more time.
Give me 1 second. It is, and it makes total sense because at the end it has to fit you, right? And it makes total sense to saying go. Well, it's fine. Like, take anything. Oh, yeah, like it has to fit you. So there is no real solution. We did not in this course say go to the robotics industry. Heck no. Or do AI? Heck no. Like what we said is, there's cool stuff out there. If you're up for it, these are the stuff which may take off.
Learn a way to identify it. Like look for these things. These 10 might take off, they might not. But you'll understand what to look for and what future technologies are.
Any other questions?
All right, shall we close it out?
Thank you.